Testing 1, 2. Everyone should have a sound check. We're going to get started in a few minutes here. Yeah, I could fly out. Everyone have their handouts? I need you to push me around. All right, good evening, everyone. Welcome to the TST January 2019 seminar. Tonight we have Brandon Steckler out. He's going to show you some neat stuff because this is not your father's Oldsmobile anymore. And as I was just speaking to someone before we started, you know, when you really look at engines today, they're not the engines of years ago. So if you have a valve train issue, you're going to have a problem trying to find it. Compression gauges, vacuum gauges that we once thought were good are no longer good on today's vehicle. So this class, or seminar we should say, Brandon's really going to show you some really neat stuff that if you don't have pressure transducers, you'll probably want to go out and get them. You know, we've had quite a few different vehicles where without the pressure transducer, a relative compression test looked perfect, compression gauge looked perfect, vacuum looks good, and you really would think there's no problem. But that's what this is. This is like the MRI that they could have used on my broken ankle into the automotive system. So again, really good setup here. We'll go at the end, we'll fill out our evaluation. You guys online, I'll send you some questions a little later on. And we'll go over our newsletter. Our next training event is obviously the TST Big Event. There is no, for you guys out in the internet land, there is no simulcast of that setup. So be aware of that. You can view it afterwards. We usually put that up. But that'll be March the 30th, 2019. We'll be at the Terrytown Hotel. We got 3 great speakers. If you go to back of your handout here, we basically have Chris Lewis from ATG. He'll be doing GTI. It's only the fingers work here. We got John Anello doing the ADAS system. And next year, John will be our headline speaker because ADAS systems are something you really need to get involved in. Whether you do wheel alignments or any type of drivability, the ADAS system can affect that. We also have John Thornton doing in-cylinder pressure transducer diagnosis. Real good class. I happen to have sat in it with real good case studies down in Florida when we were both teaching for Autologic. So real good stuff there. Full day, hot breakfast, hot lunch, and snacks throughout the day. Maybe you'll be lucky to win one of the great prizes that the vendors give away. So you want to check that out. Back of our newsletter. You guys on the internet should have received this as well. So you can download that. And we'll go through our sponsors in a second. We'll say the next monthly one is in May. Ken Zanders will be our guest speaker. We'll be in Massachusetts, Connecticut, New Jersey, New York, and on the internet. Kenny Zanders will be coming out. I forgot what class he's doing, but you can check that out on our website. And we'll go through our sponsors real quick and get Brandon on. Autel, we have OTC. We have fingers we need to get fixed. The GTC 505, great tool, by the way. You just experienced this today. And you can put your mic on. You could actually speak.
There we go. Is it working now?
I don't know. Are you unmuted? What does it say? I think you're good. Say
okay.
something.
Yeah. You guys hear me?
All right. And we got Run Right. We got Neutronics, Autologic. And by the way, when you look at some of the Autologic and DrewTech stuff, same company, have you seen their new stuff for the ADAS system and for the cars? Pretty neat setup. So you may want to check that out. Flow Dynamics. IATN and Identifix, BG, Launch, AE Tools. Let me stop at my buddy Joey there for a second. I can't really say anything bad about dealing with AE Tools. Nothing but good stuff, in fact. Because when you have a problem with a factory scan tool, and you bought it, a lot of guys go, oh, I could get that cheaper, the subscription off Honda or Ford. He gets right on your computer. His guys are really the best. I know we have a few people here that have his tools. He's the guy to buy a factory tool from. And you're not going to fix today's cars without a factory tool. And if you're not aware, what happened in 2018 with Chrysler, right? Well, Chrysler, you can only get generic information now. Doesn't matter what scan tool you have unless you got the factory tool. Oh, and you heard about taking the radio out and jerking around and going in there. Well, Chrysler already fixed that problem. So you still can't get the data on their newer cars. So get the right stuff. You can get the MicroPod 2. Joey does that whole setup throughout the country. And he sells other tools as well. CPS with Motivac and their other stuff. ATQ. And of course, one of our main sponsors for years, Bernie, with his E-Scope and the 3C machine. Have you been using it, Brian? Okay. Brian, I don't know if you could hear that, but he said he loves it because it really does work super well. Really, really good tool. Carbon buildup and GDI is a big-ass problem. So you'll want to do that. Take a look at that tool. All right. Mr. Brandon, you're all on your own. I'm going to shut up unless someone does type a question in. I'll yak it out loud. And
very good.
All yours.
For it.
Let me get the hell out of the way. I'll leave these up here because too hard unless I put it in my little basket like the Wicked Witch.
Thank you, G.
Boom. All right.
Guys, good evening. How you doing tonight? Good. I really appreciate you guys coming out tonight, especially after a long day's work. It's guys like you going to help keep the industry moving forward. Thanks for tuning in with us here at TST Seminars. My name is Brandon Steckler. I'm an instructor with CarQuest Technical Institute, World Pack Training Institute. I contribute to Motor Age magazine, but above all that, more importantly, I'm a technician just like you guys. I've been a tech for about 20 years now. I've got most of my career experience lies at the dealership level. Anybody in here have both dealership experience and independent side experience? Okay. Don't anybody take offense to this. You guys at home too. Isn't it true that we tend to get tunnel vision at the dealership level? There's only one way of doing it, right? The Ford way, or the Honda way, or the Nissan way, or the Mercedes-Benz way. I thought the same way. I was really, really good at what I did at the Honda dealership. I had a good rapport with my customers, my fellow technicians and service advisors, and I was very comfortable working on that car, but that's the key word, I was comfortable. I was good at it because I became complacent. I got used to working on them, and things became routine for me. When you start memorizing wire colors on the circuits you're going to attack, right, you're going to troubleshoot, it was time for a change for me. I didn't want to do the same thing for another 35, 40 years. So one cold evening, I reached out to my friend at the parts counter who had one of the jobbers that they hand out that a local class is going to be in town. Do you want to sit on it? I said, sure. And it was called the A, B, C's, and D's of Ignition. Anybody in here ever heard of Jim Morton? Good. Jim Morton is a phenomenal man. Cranky old guy sometimes, but I love him to death. He's like an uncle to me. Well, I got to tell you, I sat in on this class that he was delivering, and it absolutely blew my mind. I was floored because this guy knew so much about ignition systems. And it wasn't a Honda ignition system, and it wasn't a Mercedes-Benz, or it wasn't a BMW or a Ford. It was ignition systems. And he boasted that. He challenged anybody to give him a car that didn't run and had an ignition problem. He would figure out what was wrong with it in 15 minutes or less. He didn't care what it was. And the confidence he had when he walked through the door, it just, again, blew my mind. So I reached out to him, and I said, how much for some private training? And I'm not going to put you on the spot, old man, because I know what you think I'm going to say. He charged me an arm and a leg for private training, but he took me seriously after that. He took me under his wing, and he taught me everything I needed to know about learning. Not about cars, about learning. He taught me 85% of the things that happen on cars have to happen because of the physics. He didn't care how Mercedes-Benz did or how Honda did it. He taught me how a spark came about, how it was discharged. He taught me about the operation of a DC motor. He taught me about Ohm's law. Those are the things he wanted me to master. If I could master that, I could master cars. That's the 85%. The 15% is how Honda discharged that spark, or Mercedes-Benz, i.e. distributor ignition systems, 2-wire cops, 3-wire cops, 4-wire cops. You see what I'm getting at? But if I knew the physics behind it, I'd be able to figure anything out as long as I had good information, proper tooling, and I knew the limitations of my tools. If I could master those three, like a 3-legged stool, I wouldn't fall over if I had all 3 legs beneath me, right? Makes sense. You take away one of those legs, you topple sooner or later. So anyhow, from that point forward, I started to look at cars differently. I got out in the independent side of the industry, and very quickly I found out how little I actually knew about cars. I mean, I got to hand it to you guys that aren't in the dealership and are doing it on the side. I misjudged you guys. I thought the dealership level was where it's at. These guys knew more than anybody about a car. It's not necessarily true, and you guys can attest to that. So I started looking at cars differently. I decided I was going to start trying to understand how things work. And when I had to find out how Honda did it, I'd go that way, or how Mercedes-Benz did it. So then I got involved with pressure waveform analysis. Why? Because an internal combustion engine is an internal combustion engine. It's nothing more than an air pump. And if I asked you, if you lost your 19 millimeter socket today, would you go right back out tomorrow and buy one? Come on. You wouldn't?
No, it might show up somewhere.
Okay.
In my shop, it might.
Assuming it didn't. You need it.
Of course.
You need it on everything, right? You need it to get through your day. You won't make it through your day without a 19. This stuff applies to everything. Operation of a lab scope, it applies to everything. We're not talking about a factory tool. These are the tools, the techniques I'm trying to master. So that's where my concept came up with this class. I got a knack for pressure waveform analysis because I became kind of obsessed with it. I couldn't understand why all the squiggly lines appeared on the screen as they did. And as I began to study them and things began to click, I invested some time and got organized. And I realized that people could start to understand what I was seeing, and it made sense to them. So let's move forward with this, okay? Guys, I understand you guys at home too. This is an 8-hour class. We're going to squeeze as much material as we can in here in about what, G, 3.5 hours or so?
3.5 hours.
About 3.5 hours. So I want you guys to ask questions. Please reach out, ask any questions you want. I'm going to do my best to answer them. I never did this on a camera before, so it's a little different for me. But let's see what happens here.
And Brandon,
yes, please.
This is part 1.
Yes, absolutely. I forgot where I was going with this. This is part 1. G's going to have me back here next year for part 2. I couldn't give you a date yet. That'll be out soon enough. But this is part 1 today. So we're going to try a couple of things here. I'm going to try standing on this side and that side. If you guys have any problems seeing, let me know. I'll move around. So what we're going to try and cover today, what is a pressure transducer? We're going to talk about the different types of pressure transducers. We're going to be dealing with delta transducers and absolute transducers. What the technology can do for us, the information we can see without disassembling the engine, why it's a vital technique to learn and utilize. Of course, we're going to cover in-cylinder waveform analysis, how to go about analyzing it like a doctor looks at an X-ray. We're going to also talk about some auxiliary tool combinations we can use in conjunction with the waveforms themselves to help associate the waveform with the 720-degree engine cycle and elapsed time. We can make some diagnostic decisions combining these tools and techniques. We're going to look at the intake manifold vacuum waveforms and analyze them. Also from the tailpipe, the crankcase, and the cooling system. And finally, we want to be putting the puzzle pieces together. We're going to be looking at all these waveforms from all different angles and understand that they all originate from inside the combustion chamber. Everything that happens in the tailpipe, the intake manifold, sometimes the cooling system if we have cylinder head or gasket issues, in the crankcase, all that stuff happens out there because of what happens inside the combustion chamber. We're also going to talk about data acquisition and storage. To this day, I still go back and I look at some waveforms that I captured 8 years ago because I didn't know what I was doing. When I see those same exact waveforms, I could actually picture the car, what I was working on. But now I see stuff in that waveform that I never saw before. And I start making new mental connections. Does that make sense? And importance of networking. This industry is hurting for good, solid technicians. You phenomenal guys that are out there and are getting older and put your time in, you're getting out. Us younger guys getting in, we're getting in at a smaller rate than these guys are leaving. We need technicians with rock solid testing techniques and strategies, and it takes networking, reaching out to your fellow technicians, guys, whether it's on Facebook or on YouTube. I got friends all over the world, real tight-knit guys, and we are constantly sharing ideas, tools, and techniques. Heck, we were on my drive up here, we were working on a car together, all of us, all over the country. So we got a network. So somebody tell me what a pressure transducer is. What does that mean to you? A pressure transducer is nothing more than a device that can measure a physical quantity and convert it to an electrical signal. And we take that electrical signal and we interface it to our lab scope. Now we can look at it over a period of time in I'll call it a graphed format. Now the two types of pressure transducers we're going to be talking about today, I mentioned earlier, absolute transducers and delta transducers. Does anybody here know what I mean when I say absolute? Anybody? Okay, an absolute transducer is one in which that outputs a signal that's relative to the pressure or vacuum it's reading, just like a map sensor. We're all familiar with map sensors, right? That's a 3-wire sensor. That's a pressure transducer. A fuel tank pressure sensor, that's a pressure transducer. That's what these devices are. So it measures actual pressure. This one, when I say pressure transducer, I mean it's referencing positive pressure, 0 psi gauge. What that means is as pressure increases, so does the output from the transducer. Does that make sense? And vice versa, when pressure decreases, so does the output of the transducer. So when that's interfaced to a lab scope screen, if we're down here at 0 psi, and that's pressure and that's time, if we apply pressure to the positively referenced pressure transducer, the waveform's going to climb, right? You're with me? Okay, next we're going to talk about a vacuum transducer. It operates exactly the same way as the pressure transducer, but it's referenced to negative pressure. What I mean by that is, as the waveform, as the vacuum intensifies, as it gets stronger, as it gets deeper, then the waveform will climb. As vacuum decreases or decays, gets weaker, the waveform's going to drop. So in the end, if we were to take a pressure transducer and a vacuum transducer and put them, test at the same sample point, and whatever we're doing, we're cranking the engine over, we're increasing, we're decreasing pressure, they're going to go equal and opposite each other. Does that make sense? I'm telling you this because we have to be familiar with the equipment we're working with. These are some of the options you're going to have available to you as technicians purchasing these pressure transducers. Like the pressure transducer, the vacuum transducer, a 3-wire sensor, requires a reference voltage and a reference ground. This gives us our range of operation, a ceiling and a floor. And the signal, the 3rd wire, is going to report to our lab scope the atmosphere it's measuring, whether it's a pressure or at 0 psi gauge or whether it's in a state of vacuum. So anybody in here Pico users? You guys, I know there's a bunch of you guys at home that are Pico users. Those of you that are familiar with this device. This is called a WPS 500X. This is a very capable pressure transducer. It can measure very accurately. It responds very swiftly. Anywhere from minus 15 psi to 500 psi. Now that button in the middle there, it's got a pressure range that's selectable. So we can change the resolution of this sensor. We can make it more easy to view or less easy to view depending on the atmosphere we're testing in, the pressure in that environment. What's cool about it is it's a self-powered transducer. It has, if I'm not mistaken, a lithium-ion battery internal to it that you charge it in the wall, right, at a USB, mini USB, and then it can hold its energy for the better part of a day. So it's a standalone device. That's really neat. The 3 different operating ranges allows it, again, minus 15 to 500 psi. That's ideal for testing in-cylinder compression. Minus 15 to 50 psi, which is ideal for testing inside the intake manifold. And a very small scale, minus 5 to 5 psi positive, that's perfect for testing tailpipe pressure. Now, any of you guys in here are automotive test solutions users? One guy? Do you have these pressure transducers? What'd you say in the back? I didn't hear you. I'm sorry. Okay, great. Well, Bernie and ATS put out a phenomenal bunch of products, but these pressure transducers made by them, what's unique about this is these pressure transducers are powered up with a reference and a ground from the scope module itself. So you don't need an outside source to drive these devices. Does that make sense? It comes right out of the scope channels. It too is a 3-wire device reading, it's got a reference voltage, a reference ground, and the signal reporting back to our lab scope is sampling, it's tying a voltage value to the pressure or vacuum source it's measuring. This one here, this device is called a Fluke PV350. Snap-on rebadged this same device. I can't remember what the model number is, what they called it, but this is a phenomenal device. Any Snap-on users in here? You do? Okay, great. I'll use the terminology grew up on this device. When I first got into pressure waveform analysis, all I had at my disposal was an old 20-year-old Snap-on Modus. And I had this device right here. I had the Snap-on badged one, but it was the same thing. This is called a PV350. It measures both pressure and vacuum. It too is a standalone unit, except this one doesn't have a lithium-ion battery. It's got a little cheap 9-volt battery in it, so it's very cheap to maintain. Don't quote me on a price here, but I found them on eBay for $150, $200 used. So it's a great way to get into this, especially if you're a Snap-on scope user. I say Snap-on because you see these banana jacks right here? They're perfectly spaced to drop directly into the top of the Snap-on unit. There's some other cool features here. I don't know if you guys can see this on camera, my red laser. Matter of fact, if somebody would report to me through G here, let me know if you can see this. That would be beneficial to me. Right there, there's a 0 button. Did you say you are using, anybody in here using the Snap-on pressure transducer setup? Did you notice when you get a pressure waveform on the screen, you start the car, it seems to be offset, like minus 10 PSI? That's a common trait among all these Snap-on devices, every one I've experienced. You're not going to change that. The way it auto-zeros, it automatically offsets it negatively. To combat that, you can go ahead and grab this knob here. Once you get a waveform on the screen, and like Tune in Tokyo, right, you can turn the knob until you get your 0 point accurate. So it's going to work out for you there. It's really beneficial. This produces a phenomenal waveform on a Snap-on device. Now, something else that's cool about it is this switch here not only turns the device on, but you can put it in a scale for pressure, as in for pounds per square inch, PSI, or KPA, kilopascals. Here's what I'm getting at. KPA is 3.38 times more resolute than pounds per square inch. You guys remember connect the dots, right? What's this look like here? What's that picture look like? Come on, guys, don't be scared.
Smiley face.
What is this? What's this picture right here? What is it?
Car.
It's a car. Great, thank you very much. If I took away half of those dots or a third of those dots, would that look much like a car? Probably not. That's what I'm getting at. By putting that Fluke PV350 in KPA mode, you're going to get 3 times as many dots. It paints a prettier picture. So it's a very good device to couple to a Snap-on, in my experience. Snap-on also has their own pressure transducers that they make. Does anybody own them? What do you think of it? I asked you. I didn't tell you that. You said that. You volunteered that information. My experience is I was not pleased with the operation of it compared to what I can get performance-wise out of that standalone PV350. The Snap-on devices, what's cool about them is they come in a 0 to 100 PSI and a 0 to 500 PSI. The 0 to 100 PSI is going to give us some great resolution. The problem is, what's cranking compression go to on most vehicles? Heck, on all vehicles. Above 100, right?
Should be.
That's not going to do us any good. So we go ahead and pop the 0 to 500 PSI transducer in there. Now what? Those same dots we had, we got to stretch them out over a range of 500 PSI. What's that do to our waveform? Makes it nice and soft. It takes away all those little details that we want to see. On top of that, it plugs into the scope module, which is really neat here, this auxiliary port. What that serves to do on your Snap-on scope is it drives the transducer. It provides the reference voltage, the reference ground, and then it converts the voltage signature coming off of that transducer to an actual pressure value. So it displays on your scope as 70 PSI or 120 PSI, not 0.78 volts. See what I'm saying? But there's a downside to this. That 0 to 100 PSI transducer, you guys see that? I know we didn't get much into the waveforms yet, but you see this flat part here? This transducer bottoms out at 0. It's totally useless for analysis because we need to see vacuum. We need to see below 0 PSI gauge so we can see when valve events and things like that occur. Without that, this is totally useless to me. So I got away from these Snap-on transducers. I'm not knocking Snap-on. I'm just saying they don't do what they're supposed to do in this application. We're going to talk about some delta transducers. What does delta mean? What's the word delta mean?
The difference between.
Right, change, right? The difference between two things. Now there's 2 devices I have here. On the left here is the first look sensor. It's a delta transducer. It responds to changes in pressure only. It doesn't deliver a value like an absolute pressure transducer does. Now first look sensor, the word first look is nothing more than a brand name, like Kleenex is to tissue or Nike is to sneakers. First look is a brand name. The device, the name of the device is a delta pressure transducer. There's another one that was on the right side of the screen, serves the same purpose, called a pressure pulse sensor. That's made by a company out in Bulgaria called Autoditex. The difference is the one on the right side of the screen was like 25% the cost as the other one. But they both work. I have them both, and they both work very well. So just keep that in mind as you're getting into this type of testing. Now, they're both piezoelectric devices. Does anybody know what I mean by that word, piezoelectric? You guys?
Same as a knock sensor.
Right, same as a knock sensor, the same technology. It's used the same way. Our gas grills at home, you know the striker? Bang, 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 and then you got fire. There's something in there that strikes a crystal the piezoelectric crystal that when it's excited, it outputs a voltage. So what's great about that is the harder you strike this crystal, the bigger the voltage. And we're going to capitalize on that technology inside this device here. As as pressure is applied to this device, it will output an AC voltage in a positive direction, right? Sloping upwards. If a vacuum is applied to this device, it'll slope downwards. Does that make sense? The harder you push, the more pressure you push on it, or the more vacuum, the taller the signature will be. So not only does it show direction, but it also shows intensity. It's very, very, very sensitive. This device is so sensitive, if I have my lab scope set up on the right voltage scale, and I held this pointed towards you and somebody was talking to me, if I interface that with a lab scope, I could see your voice, the sound waves coming across the air here on my scope. So we're going to capitalize on this technology to help us make some diagnostic decisions, looking at changes in pressure. I got to show you something here. So just to recap, positive change in sensor output reflects positive change in pressure. A negative change in sensor output reflects a negative change in pressure. The amplitude of the sensor output is proportional to the amount of pressure change. So I want to do something here to demonstrate by case in point the difference between the output of an absolute pressure transducer compared to that of a delta transducer. I call this little experiment a shootout. And I don't know, G, can you see that pretty well on screen there?
Yep.
Okay. On the left side of the screen here, I have my absolute pressure transducer. On the right side is my delta. This reports a value, and that reports only change. You can see they're connected to a vacuum hose with a T, and I'm on the end of this common hose here where I'm going to be applying pressure and vacuum, and we're going to see how the two sensors respond, okay? If I lose anybody, stop me, please. So here's an experiment. I've got a scope here with two different channels on it. The yellow is going to be of my absolute pressure transducer, and a delta from my, the red trace is going to represent my delta transducer. How well is this coming in, G? Can you see that? A bit tough? Okay, well you guys are just going to have to watch my fingers. So here's 0. We're going to look at the yellow one first. I'm going to take this hose here, and I'm going to put it into a state of vacuum. I'm going to put my thumb over the end of it. So there's vacuum trapped in this hose. The signal pulled down, right? And it held, and it held, and it held. And the moment I took my thumb off the end of that hose, look what happened to the sensor output. See how it went high? It returned back to 0, didn't it? Can you see okay? Then I waited a few seconds at 0 gauge, atmospheric, and then I went, and I filled that hose up with pressure. And I held it. Isn't it above 0 there? It's about 2.5 psi there. It's holding. It's holding. It's holding. I'm going to come on this side now. And then what did I do here? What happened right here? I let go of my thumb, so it returned back to 0. You see how that worked? It reflects the actual pressure value. I know this is really hard to see on camera because of the lights, but watch my finger. So here we did, I got to come on this side again. Here we did the same thing. Now with the red trace, I went, and I held it, but watch my finger, it went, and it came back. Why did it come back to 0?
No more change.
No more change. The change was when I pulled pressure, reduced pressure in the hose, and then I stopped reducing pressure, right? I put my thumb on it so it returned. So there's no change right now. I'm holding it. And then I let go. What happened to the signal? It went up and then what? It came back down. Why? No change, right? We stopped changing. Then I waited a little bit and I put pressure in it. Which way is the signal going to go when I put pressure in it? Up. And then what's going to happen as soon as it goes up? It's going to come up and come down. If I lost anybody on camera, please report to G. And then I waited a few minutes, a few seconds, and I took my thumb off of it. What do you think happened? It went down and came back up. So you see how the two different sensors, their operating characteristics are different, right? We have to know our equipment. Now that I know how the tools function, we can apply these techniques to cars, to other experiments. If I didn't know that, couldn't that screw you up?
Sure.
It could, big time. You got to know how they work. That's where the terminology delta comes into play. So just to show you something really neat that Bernie Thompson in Automotive Test Solutions does, that's pretty unique. Down here in the bottom is an FLS sensor. Up top is their 25 inches of water pressure sensor. Now, roundabout figures, there's 25 inches of water in 1 inch of mercury. So it's 25 times more resolute, right, when we're talking about vacuum waveforms. Just for grins, I took both of these devices and I stuck them in a tailpipe of a perfectly running car. And what I'm trying to show you here is they look almost identical. Their rate of change is about the same. The difference is the FLS only reports change, whereas the inches of water transducer reports what? Absolute pressure. So I can attach a number. This means so much vacuum and so much pressure. That could have some benefits. You guys will see, not so much tonight, but in part 2 where this was more beneficial than an FLS. So the yellow trace is the inches of water transducer. The green trace is the FLS. The red trace here is very hard to see on camera because I know that because I'm having trouble seeing it now. But right here is an ignition event. Okay, it's about this tall. In the same spot here on the green channel, that ignition event looks this big. That's because I was just playing games with the voltage levels on the scope to make the waveforms appear to be the same size. Okay? So Pico gives you this similar functionality on the WPS. Through certain zoom levels pressure levels and zoom modes, you can generate the same level of resolution and response time using this device as well. I'm not as familiar with this. If anybody wants to comment, G will read it to me and I'll say it out loud, but they give very similar capabilities if you get them dialed in just right. What are these things? Paddles, right? Remember when you were a kid, you pick up the paddle and how many whacks can you get out of that ball? Like 1, right? That's about it. Doing this stuff, right? So my point is, if I were to take this paddle and I got that ball and I made contact with the ball and I hit it very lightly, the ball is going to come out and then what it's going to do? It's going to come back, right? Maybe not very far, but what if I took that ball and I really gave it a whack? What would happen then? How far would that fly back? Pretty far, right? There's a characteristic, I don't know what the terminology really is, but I call it the bounce back characteristic. With the FLS sensors, the further that sensor signal deviates away from the 0 mark, they're going to fly back. If you didn't know that, could that screw up your diagnosis? You better believe it. So I'm trying to show you some of the characteristics I've noticed, some of the pitfalls I've had learning this technique. And the end result is once you learn what these tools are supposed to do, just like any other tool's limitation, you can start applying them successfully. This is a bit inappropriate, I'll admit that. But I'm just trying to make a joke and hammer home a point. Experimentation is healthy. We have to play with our tools. That didn't come out right. We got to use these devices and experiment with them, not on live vehicles. We don't want to look at these with broken cars yet. We're not ready for that. You're going to get your butts handed to you. So you have to take out the scopes. You got to call him and you guys got to grab a pizza and stay late after work one night and just mess around with this stuff. Matter of fact, that's what I did today with my good friend Eric Dibbler up at his shop. While we were killing some time, we spent all day playing in the shop with these things, having some fun. So pressure transducer application. Of course, we're going to be looking at in-cylinder pressure testing, but you can also use it in the intake manifold, in the tailpipe, the crankcase, the radiator. I want to ask you guys something. Mechanical compression gauge, what does that do? What does that do for us? What does it show us? It's not a trick question.
Peak pressure.
Peak pressure. So a scenario here. You guys at home, I'm going to ask you guys this too. If I'm cranking an engine over, and let's say for giggles I have 100 PSI every time that cylinder cycles, crank, 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 and I crank it over 10 times. But on the 8th time, my exhaust valve fails to seat. I don't know why. It just doesn't seat right, and I only make 60 PSI of compression. What's my compression gauge going to show me?
The same shit.
The same, 100, right? Yeah. For that reason alone is why I took my pressure gauge and I threw it all the way across the shop. And I'll never use it again because it will let me down. It has let me down. Using a pressure transducer allows us to take that same pressure, convert it to an electrical signal, and plot it over time. So that gives us a history. And because it's on a lap scope, we can associate it with elapsed time, can't we? So if I know what 720 degrees is, right? Compression to compression tower, and I know how much time went by, can I figure out how many degrees occurred in each millisecond? We're going to cover that later. I can. It now has bigger value. There's a lot more data available to me simply by converting that thing to an electrical signal. A pressure transducer and a lap scope is going to be a powerful combination for you. So it displays much more than just peak pressure. Works with other inputs and tools to provide correlation in time to the 720-degree engine cycle. Again, applying cursors. First of all, who has a lap scope here without cursors? Oh, good. If you do have one without cursors, you need a new lap scope. You have to have cursors. You have to have the ability to attach time and associate it to the 720-degree engine cycle. So again, this allows for preliminary and rapid verification of engine mechanical integrity, even with pinpoint accuracy once you start getting used to looking at this stuff. It's phenomenal. But the key to this whole thing is it's preliminary analysis without expensive disassembly. And we're going to go through some examples later on in class where this comes in real handy. You see the value in it. So what can it tell us? This is amazing. Once you guys really get good with these techniques, your minds are going to be blown. It can show us valve sealing issues, compromised piston rings and walls, damaged bent connecting rods that don't get a full stroke, exhaust restrictions, heavily carbon valve restriction. I'm working on some projects right now involving testing for GDI problems. You can see carbon in these valve ports through the eyes of the pressure transducer interface to the intake manifold. You can. And I'm working on that right now. We're going to be putting it in my next series in this class. You can monitor cam phasing dynamically. Compromised valve lift and duration due to cam lifter failures. We're talking about hydraulic lifters that collapse or cam lobes that are worn flat or have spun on the camshaft. How hard is that to diagnose sometimes? Right? You can see all that stuff through the eyes of a pressure transducer if you know what you're looking at. Ignition timing. So let's move on. Everything that happens in with these waveforms anywhere in the vehicle, when I say anywhere, I mean in the intake, in the tailpipe, in the crankcase, in the radiator, it all starts in cylinder. So of course it's only natural to start with in-cylinder waveform analysis. That's where we're going to begin. Let's not overcomplicate this. This is a lab scope. The lab scope is going to show whatever domain you're in, registered on the south to north axis here, and times registered horizontally. So this is nothing more than pressure over time. It's as simple as that. Don't make it scary. It's not at all. And another thing, I want you guys to stop thinking about pressure when you're talking about pressure transducers. I know that sounds ridiculous. Start thinking of things about volume. I'll explain here in a minute. Check this out. Uh-oh. There we go. This is a syringe. Pay attention to this analogy. Once you understand this analogy, you understand pressure waveform analysis. If I had this syringe in my hand, right, and I pulled that plunger all the way extended, and I held it above my head, okay, how much pressure is in this syringe relative to the pressure in this room? None. 0 psi gauge, right? But it's full of what? It's full of air. So if I took this syringe here and I put my thumb over the end of the syringe and I took that plunger and I shoved it all the way to the top, what happened to the area inside that syringe? The area got smaller. So if no air came out and the area got smaller, what absolutely had to happen to pressure? It's physics, you can't change it.
Increase.
Pressure had to go up, right? So that same scenario, if nothing came out and I took that plunger and I pulled it all the way back to where I started, what will pressure be in that syringe? Back to zero. Or back to where we started, right? That's what you got here. 0, we plug it, we push the plunger up, we get, let's say, 100 psi, nice round number, and then we pull the plunger back down where it's 0. Let's change this up a little bit. Same scenario, but this time when I get the plunger close to the top, some of the air kind of comes out, right? The thing burps a little bit. Just a little bit of air. So instead of producing 100 psi, I was only capable of squeezing enough air to produce 80 psi. If I pulled that plunger back down again, doesn't it make sense that I would get down to 0 psi before I got all the way back down to the bottom?
Yeah.
Okay, that's part A. Part B, what would happen if I kept going?
Vacuum.
A vacuum, exactly. That's what's happening here. So this is what a cylinder looks like. This is how a cylinder behaves when it loses some of its charge. And this is going to make sense when I start putting pressure waveforms up on the screen. Did you guys understand that?
Yeah.
Okay, good. If you understand that, you can understand pressure waveform analysis. If you can't understand this, we have to stop and cover it again. Just a reminder here, for those of you that are not too familiar with lab scopes, anything that happens on a lab scope to the left of a certain point happens early or advanced. Anything that happens to the right side of any point on that lab scope is late or retarded. Make sense? I know it seems obvious, but we have to remember that when we're looking at anything on a lab scope. So let's get into the different strokes, okay? You might not know what I'm talking about, but when I break down this waveform, you're going to understand. Gee, can you see that on the screen? Mm-hmm. Okay, good. I was worried about this one. I'm going to start on the left side of the screen here. This is, in my mind, a picture-perfect, textbook-perfect, in-cylinder running compression waveform. This thing's beautiful. There's nothing wrong with this at all. So let's associate this with a syringe for a moment. We talked about that syringe. If I held it over my head, it had 0 psi in it. Pretend that syringe is a cylinder. And this running cylinder, can we use 20 inches of mercury as a nice good manifold vacuum number? Just for the sake of argument. Those of you guys up in the mountains, that might seem like a weird number to you, but down here at sea level, that's 20 inches of mercury is a pretty good number. But we're just going to use that number because it's a nice round number, so just bear with me here. And for the record, minus 20 inches of mercury is about minus 10 psi, just in case you didn't know that. So if I start off with minus 20 inches of mercury, again, my syringe open, and I come over here and I close it off, right? And I trap 20 inches of mercury in there. And I push the plunger all the way up. And I produce pressure, but nothing comes out. And then I take that plunger and I pull it all the way down. How much pressure should be in that syringe now? 0. Where we started, which was what? Minus 20 inches of mercury. Okay? So check this out. I started at minus 20. First of all, this thing keeps repeating over and over again. So watch my finger here. This point right here is the same point on this side of the screen. You guys with me? So I started with minus 20. Okay, that's over here. I closed the valves, the intake valve, right? That's me putting my thumb over the syringe. The piston starts heading up. It's the same as me pushing the plunger up. I squeeze whatever contents is in there. Then I pull the piston back down. Okay, that's your expansion stroke. Piston's heading down. Why am I calling it an expansion stroke? Why am I not calling it a power stroke? There's no fire, right? No combustion. The spark plug's out of the cylinder. Remember, we're replacing our mechanical compression gauge with a pressure transducer. We're in the spark plug hole now. So I come back down to minus 20 inches of mercury. Okay. What happened here? Don't anybody tell me what they think happened with the engine. We're talking about pressure here. If this is pressure and this is time, this tells me pressure changed. Pressure went up in a very short period of time, doesn't it? Does that make sense?
When the piston came back up and started pushing exhaust out.
Before the piston started moving, if this is bottom dead center 180, that's when the piston comes all the way down. Their change happened earlier, before. What valve opens right before we begin the exhaust stroke? The exhaust valve. Do you think this change in pressure holds some significance here? What happened right there with my finger? The exhaust valve opened. We saw a change in pressure, right? That's what we want to see here. So right here at the bottom dead center mark is where our piston changed direction from descending to ascending. Piston's heading up. Why am I not building pressure here?
This valve's open.
The exhaust valve's open, right? The piston is no longer squeezing the contents of the exhaust. It's displacing the contents of the exhaust. It's pushing it out the exhaust port, okay? Then we get over here to top dead center 360 when the piston's all the way at the top. And then right before it changes direction, something happens here. What happens to pressure right here? What happens to pressure right here?
Decreases.
Pressure decreases. We go back to 20 inches of mercury. Well, my piston hasn't even moved yet. Why do I have vacuum in the cylinder? What happened right here?
Exhaust valve closed.
Not yet. What happened right here to introduce vacuum to the cylinder?
Intake valve open.
The intake valve open. Remember, this engine's running. We got 20 inches of mercury in that big storage tank, storage tank called an intake manifold. The intake valve open right here. So that point holds some significance, doesn't it? Well, then we come all the way down here, okay? From this point, 360, to this point, 540, our piston is descending. So it starts contributing to that intake manifold vacuum. It's its turn to pull on the manifold. Till it gets to 540, that's when the piston stops moving and changes directions. Well, the piston starts heading up right here. Why isn't pressure going up here? What valve? The intake valve's still open. So let me get this straight. Pressure did start to build right here. What had to happen at this point? Think this point holds some significance here? A lot amount. You better believe it. So as you can see here, by placing this waveform, coupling it to a lap scoping and putting it over on a screen over a period of time, we can see valves opening and closing. This is just the start of it. But is it starting to make sense a little bit? Okay, let's move forward. When I'm looking at a good running compression waveform in this case, or a cranking compression waveform, I want to see a bunch of things. I call these points of interest. At the top of this scope capture, you're going to see good running compression. This one here is about 65, 70 psi. I will tell you this, running compression is usually about half of cranking compression. Anybody know why?
Time.
Time. Right.
Much faster.
So when the piston's cranking, there's a lot more time to fill this cylinder, isn't there? And if I get more air in the cylinder, I take up more space. When I squeeze those contents, I get more pressure.
It's also dealing with intake manifold lower pressure versus atmospheric pressure.
Right, when you're cranking, you're not fighting the restriction of the throttle plate. Very good point, thank you. So I have good running compression. It's going to be different for every engine, depending on specification, how the engine's built, the stroke of the motors, things like that. But we want to see good running compression, whatever that is. We want to see straight towers. We didn't talk about that just yet. We will in a minute. We want to see defined valve events, right? We never want to see anything happen soft and slow. Remember, this is pressure over time. We want to see rapid changes in pressure, meaning this, things to drop real fast, just like that. When we see things happening slowly, that means valves aren't seating right, or they're too tight. Does that make sense? Mm-hmm. Or they didn't open at all. Another thing here, even pockets. Go back to that syringe analogy. We started with this, we finished with this, right? Those pockets are even. That's the takeaway from it. That's a sign that there's no leakage in the cylinder, because if I had leakage, what would happen to this pocket here? It would drop, right? We'd go into a vacuum. We'd start here at 20 inches of mercury. We'd go up on compression. We'd lose some contents. And then when we came back down here, we'd be in a deep vacuum, wouldn't we? Just like we did in our example. So that would cause uneven pockets. These are even, saying what? Did any contents leak out of the cylinder? They did not. When you start to get a leak that's really bad, this is going to lean to the right, okay? They call that leaning towers. Yes, do you have a question?
What's your acceptable difference in start to
In the pocket, I call it pocket differential. Typically 2 to 3 psi is normal.
Okay.
So if you were to put a cursor here and a cursor here, and the difference was within 2 or 3 psi, and lots of times it's even less than that when they're good. But when they start getting bad, you really see 4 and 5 and 8 and heck 16 sometimes when they get real bad. But leaning towers, let's talk about this for a second. Think of this as pressure over time. This whole thing's about pressure over time. Let's keep it easy. Assuming the crankshaft is turning at the same 800 RPMs the entire time this car is idling. If I build pressure at a certain rate and there's nothing wrong with the cylinder, as that piston comes back down, it should descend, of course, at the same speed as it went up. I should lose pressure at the same rate. Wouldn't you agree?
Yeah.
So if I drew a line down the center of this with a cursor, and bear with me at home because I know you guys can't see this here. I've got a horizontal cursor going this way and a vertical cursor going this way. See these two arrows? If I measure the time difference between here and here and came up with, let's say, 33.21 milliseconds of time between here and here, and then I went to the right side and did the same thing, that's got 32.12. There's only 1 millisecond of difference, which isn't very much. Now, I can't give you a nice number, but after you look at a bunch of these, you realize that's not a lot. But check this out. We call that a straight tower or a symmetrical tower. Look when things go bad. 21.27 milliseconds from here to here, meaning that infers the angle here. You go to the right side, we're only at 16.5 seconds. This is 5 times as slow as the other one, the slow to change. So if I draw the center of this, there's more meat on this side than there is this side. The waveform kind of does like this. Don't you agree? We call that a leaning tower. And believe me, if you could see these cursors, it would be a lot more apparent. That indicates there's something mechanically not sound with this engine and it's shedding some of its contents. That's very hard to tell. You're likely correct, but there's nothing in here to indicate that because you can't see the other pocket too well. Okay, you can, yeah, you can a bit. You're right. But you bring up a good point because you are going to see pocket differential a lot more easily than you will leaning towers, meaning that's going to show up first. It's kind of like you smell smoke before you see fire. Same thing. So a leaning tower versus a straight tower. Towers represent pressure changing over time. With piston speed roughly the same as it should be because the crankshaft, we're at, let's say, 800 RPMs at idle. Pressure should rise and should fall at approximately the same rate. This should yield straight or symmetrical towers. Leaning towers show a change of rate, signifying a loss of volume or a change in piston speed. I do want to bring something up though. If you have an engine, you're doing this type of analysis, let's say cranking compression waveform or cranking vacuum waveform. If your engine's popping and sputtering and kicking and carrying on, these don't count. You can't look at it. You need a nice steady cranking cadence. Engine speed directly affects pressure because it affects how well a cylinder fills. And anything that goes on in the cylinder is going to affect any other area in the vehicle. So you need steady cranking cadence or steady running engine. If an engine's going up and down and it's barely idling, you're going to have a hard time analyzing pressure waveforms. I'm going to tell you this right now. So volume loss is typically accompanied by uneven pockets, and those will show up first. And if it gets bad enough, you will see towers begin to lean. So let's get into some in-cylinder waveform analysis. First of all, what's the strategy here? We're going to be monitoring pressure changes over time. Okay? The waveform, of course, is going to be referenced to 0 psi gauge, or the atmospheric pressure. We're going to correlate the timing events with the 720-degree engine cycle. We're going to monitor for pressure differentials by moving volume through a restriction. That's all it is. It's as simple as that. And we're going to do that by using cursors to aid in this analysis. It's going to make counting the degrees per millisecond possible. So I don't know if you can see this on camera here, but right now I'm demonstrating at Automotive Test Solutions. This is an eScope Pro. It's an 8-trace lab scope, highly capable. It produces a beautiful picture regarding pressure waveform analysis because of its vertical resolution. But what we can do is first, we'd go ahead and click our cursors button, and we take our white cursors, we take one vertical cursor and we put it over here and drop it down to the center of a compression tower. And then we take our second cursor and we'd put it over here, 720 degrees later, and drop it down the center of our other compression tower. And then we come up here and click this button that I have encircled in yellow. Click this button over here. It's labeled Mark Camshaft. And what that will do is it will plot cursors evenly spaced across this waveform from the point you reference with your measuring cursors. And what it provides for us over here is 4 partitions. Why 4? I'm looking in-cylinder and an in-cylinder pressure waveform. Why do I want 4 partitions? What do the 4 partitions signify? The 4 strokes of an engine. That's exactly it. Thank you. Suck, squeeze, bang, and blow. Now, if I wanted to look at an intake waveform, or a tailpipe waveform, or a crankcase waveform, or even pressure in a radiator if I thought I had an overheating condition, a compromised cylinder head or sealing surface, I want to see how all cylinders in that engine associate with that portion of the system, don't I? So in this case, if this were an 8-cylinder engine, I would reference my vertical cursors the same way, except this time, rather than clicking Mark Camshaft to make 4 partitions for each stroke of the engine, I would simply configure this scope for how many cylinders this engine has, and in this case I chose 8, and then I clicked Mark Cylinders over here. And it will plot, in this case, again, 8-cylinder engine's chosen, 8 partitions. What I want to see using these 8 partitions is how each cylinder in this engine is affecting whatever area we're interested in viewing, whether it's the intake, the tailpipe, the crankcase. You with me so far? So let's break this down. If I know the waveform on the screen, yes, do you have a question?
This would be obviously not used for in-cylinder testing, right? This would be more intake manifold, because you couldn't scope all 8 cylinders and have a car still running.
That's correct. What I'm talking about is here. When we went back, what you're seeing here displayed here, when we press the Mark Camshaft button, and that's just for this scope here.
That would be in-cylinder.
In-cylinder.
But the Mark.
Right. The Mark Cylinders button is what I want to use when I'm trying to analyze an area that's common to all the cylinders.
Intake manifold.
The intake manifold, the tailpipe, right? Yes. So you would use this Mark Camshaft when you're in cylinder. You'd use Mark Cylinders when you're trying to analyze how each cylinder is affecting a specific area. So what we do is this. The idea behind cursors is this. We know if I have 2 compression peaks on the screen, how many crankshaft rotations is that? 2, right? Because it's a full engine cycle. And we know a full engine cycle is 720 degrees. So if I stretch these cursors from here to here, isn't that 720 degrees? If I take 720 and I cut it in half, what is that? 360, right? If I take 360 and cut it in half, what is that? If I take 180 and cut it in 6, what is that? Oh, wow, you got it. Okay. So, there it is. 30 degrees, 30 degrees per partition. Why do I have so many partitions there? Because it's a lot easier on the eyes to associate any kind of event that occurs, whether it's a valve opening or a valve closing or even ignition timing, how close it relates to a top dead center or bottom dead center mark. Think about it. When we read a cam card, any kind of specification regarding an engine, we're talking about valve opening or closing. They reference a top dead center or a bottom dead center mark, right? So I want to be able to know, am I 30 degrees before bottom dead center, or am I 60 degrees before, or am I, excuse me, am I 30 degrees after top dead center? Do you see what I'm getting at? That's why we do these cursors. That's how they're going to work for us. Picoscope. For you Pico users, you have the same capability with your Picoscope. This green ball here represents cursor number 1 to help us plot a trace for our partition. So what I'll do is I would take this and drag it to the center of that tower. And directly underneath this one is another green ball. And I drag that green ball and drop the cursor right down the center of this tower. And then I come over here to this rulers tab, and I click on that, and I have the ability to add as many partitions as I like. So I can click 1 or 2 or 3 or 4 or 10. But we're analyzing in cylinder. How many strokes in a motor? In an engine cycle? 4. So how many partitions do I want? I want 4. So I click 4, I hit go, and it automatically spaces them on the screen. What's neat about this device is this Picoscope is, I could then take a vertical measuring cursor here, highlighted by this black hollow box, and I can drag that to anywhere I'm interested in this event. Let's say right here where EVO occurs, exhaust valve opening. This scope, since it already knows how much elapsed time is on the screen, and we just told it how many degrees, or how far 720 degrees is, just by simply dragging this cursor over, it will automatically tell me where I place it, how many degrees before or after, from your other cursor it is. So if I put one cursor on 180, and I put this one here at exhaust valve opening, it will say something like 32 or 35 or 45 degrees before bottom dead center. I just got off the phone with Bernie Thompson yesterday. We had a nice conversation about some really cool features coming out.
Would have never guessed.
Okay, yeah, right? Always evolving. And Bernie is doing something now with the software that automatically calculates, just like we're talking about here. It automatically calculates degrees for you, so it's getting even easier to use. A lot more efficient.
We have a comment here. I was taught to use the crank signal to determine degrees if accuracy was needed.
Yes, that's true. A crank signal is going to give you a lot more accuracy because it's a Hall effect sensor, typically, or an AC generated voltage. And it is going to give you a lot more accuracy as compared to pressure. But remember, when we're talking about pressure, peak pressure is always going to be top dead center. And if I know this is top dead center and that's top dead center, we know that's a full engine cycle. So it has to be 720 degrees. I hope that makes sense for you. If I take that 720 and I divide it evenly, you have no choice but to be accurate. So if that doesn't make sense to you, get back to G and he'll throw an egg at me or something. Okay, so you guys with me so far on this? Okay, so using cursors to aid in analysis, which is going to use to plot the time for 720 degrees. It's going to be used to find the point of an event or how long an event lasts, the duration. This will quickly also prove out ignition timing as a potential fault. And we're going to show you how to calculate this stuff later on. It's going to be used to find differences and changes in pressure when we use horizontal cursors. This will allow us to correlate time with degrees of crankshaft rotation. It will provide a visual representation of event timing and duration, a comparison of one cylinder to another, and it varies by engine design. Check this out. This is what I'm talking about here. I was very hesitant to present this slide because everything I say on this slide you have to take with a grain of salt. Okay? I'm about to offer rules of thumb in regards to valve opening and valve closing specifications. Understand up front, it varies greatly between different engine designs. Whether an engine has active variable valve timing versus targeted, things like that. Whether it's turbocharged, these engineers are designing engines to breathe at different rates. They have different volumetric efficiencies at different RPM and load ranges. So how they design the camshaft profiles can differ from one thing to another, from one engine design to another. So when I say 45 degrees before bottom dead center, I'd say that's a good roundabout number. That's when an exhaust valve typically opens. But I've seen them go as high as 60 degrees beforehand and still be okay. Or even as early as 30 or late as 30 degrees before bottom dead center and have nothing wrong. But on a different engine, that could be way off. But there's different areas of the waveform that we're going to look at to help tell us if that's okay or not. So don't panic. So exhaust valve opening, otherwise known as EVO, typically occurs approximately 45 degrees before bottom dead center. Intake valve opening, otherwise known as IVO, occurs approximately approximately at top dead center of the exhaust stroke at that 360 mark. Exhaust valve closing is very, very difficult to see. Matter of fact, it's so difficult to see, it's unreliable, and I don't even try and find it. It has nothing to do with my analytical approach at all. I ignore it. If you see it, it's probably a fluke. Don't even look for it. It's not going to help you. But what will help you is deepest vacuum. Right after the intake valve opens and pressure drops, where that point is at its lowest, we call that deepest vacuum. That holds some significance, and that'll help infer cam timing. We'll talk about that as we move forward here.
Brandon, question.
Yes, sir. Please.
Is it best to do these tests with the VVT solenoids unplugged?
Unless called upon, I wouldn't unplug anything. I'd like to leave engines as they are, especially if you can compare to a known good waveform, a known good capture. I wouldn't disable anything.
One more. That information, valve timing, is sometimes hard to get. Any suggestions?
Yes, that information is very hard to get, and great question, by the way. You bring up a very valid point here. Not only is it difficult to get, and it's not offered on a lot of engines, probably most of them. If you find it, great. But here's the problem. My idea of open when a valve opens and your idea of when a valve opens can be different. Some of these engineers, a guy who wrote that engine book, Haywood, says a valve opens when it leaves its seat. I don't remember the number he gave, 50 thousandths, but somebody else says a valve is open when it's a couple of millimeters open. So that's going to affect timing. So I never reference those cards. You know what I mean? If we're off, if we've got a chain that's stretched, we're going to see these waveforms move. If we got a chain that's jumped, it's going to jump 10, 15 degrees. Yeah. So yeah, it's going to be off considerably.
Another comment. Most VVT systems aren't activated during low cranking oil pressures or at idle.
This is very true. We want very little overlap when we're cranking these engine over, unless it's designed that way. That not a way I can think of, unless it's some way to assist to lower compression to aid in startup. Again, I'm not aware of that, but no. Typically, we don't want overlap when we're trying to start the car. We don't want a lot of exhaust gas filling the cylinder. Good point.
And then another comment here, you could have a stuck solenoid or phaser, which is a good point as well.
Absolutely. And we're going to talk about a diagnostic approach. Understand, this is not preliminary. We don't pull a car into our bay and start taking spark plugs out and testing for pressure waveforms. That's something that we're led to by way of other easier to perform tests. We call them generalized tests.
This is level 2 and level 3 diagnosis.
This is exactly it. We're led here from easier to perform tests.
And
we'll cover that.
A couple of more. These guys
Please.
are on a home run here.
That's fine.
Running compression test and cranking compression test. The difference between running and cranking would also be seen, I guess. With
Yes, understand, for the same reason when we put a vacuum gauge on an intake manifold and we crank an engine over and we produce 1 or 2 inches of mercury, that same engine, when the engine's running and you've got some piston speed going, it's going to pull a deep vacuum. And what vacuum simply is the piston's attempting to inhale more air than the throttle plate's willing to allow. So you're right, cranking waveforms are going to produce a lot different picture than a running waveform. And we're going to talk about that as we move forward. But thank you for bringing that up. Great point. You have any more? You good?
No.
Okay.
Good.
So again, just to recap, cam and valve timing differs from vehicle to vehicle and should be compared to known good captures whenever possible if you're unsure about what these should be. But again, we're going to be analyzing waveforms. I'm not so much concerned with what the numbers show me. I don't care what the spec is in a book. The waveforms are going to tell me whether this engine's breathing properly or not. And by the end of this class, you guys are going to understand what I'm talking about. So now let's get into some examples here. Bear with me here. This is going to be a little bit tough to swallow at first, but if you guys stick with me and understand and relate everything we're talking about to that syringe, we're going to get through this okay. So this would be an example of normal cam timing. Gee, how's that look? Okay? So I got, again, good running compression. This one happens to boast 84 PSI. Again, roughly half of what cranking compression should be because there's a change in engine speed. We got straight towers and we got even pockets. Why?
Because it's sound.
Because it's sound, meaning what? The engine's not, or the cylinder's, it's not leaking, it's sealed. We didn't lose any volume. And we have defined exhaust valve opening, which is occurring on this engine. If this is bottom dead center, and each one of these are 30, if that's 30, that's 60, right? We're just about at the first one here, so that's about 30 degrees before bottom dead center. Obviously, it's good for this engine. If it wasn't, we'd have some pocket differential, and we'll talk about that. We see the intake valve opening right here. Isn't that a nice, crisp, sharp transition? Shoots straight up, right? It's not nice and round, it's sharp. It indicates a valve open like that. That's what we want to see. Same here. A sharp transition. We go from top dead center, the intake valve opens, boom, instantly we're introduced to value. The pressure waveform says pressure dropped drastically in a very short period of time. And again, we got no pressure, and all of a sudden, boom, pressure starts to build. Why? Our intake valve closed. Does that make sense?
Yep.
And peak vacuum here. We see this typically fall somewhere in the neighborhood of 40 degrees after top dead center of the exhaust stroke here. Right? If our exhaust cam was closing late and we couldn't pull a strong vacuum, when that exhaust cam finally did close, wouldn't our deepest vacuum be later? That's what I'm getting at. And we'll show some examples as we move forward here. So this would be an example of late cam timing. Now in this configuration here, this is of a single overhead camshaft design. What's the significance of single overhead cam? What's that mean regarding intake and exhaust?
One cam does both.
One cam does both. So anything that happens on the exhaust side is also going to happen on the intake side, right? We got to keep stuff like this in mind when we're analyzing these waveforms. Excuse me, engine design. So we have low compression. Why would I have low compression? I want you to think about the syringe analogy. If I have that syringe in my hand and I have late cam timing and it's single overhead cam, the exhaust cam is going to be late, but so is the intake, the exhaust valves are going to be late, but so is the intake. So if I have my syringe here, right, and I was going to push the syringe up and trap that air, if I would normally close, let me find a point of reference to point to. Let's call this the stroke of the syringe right here because it's easier to see on camera. If I would normally close the intake valve here, and from this point forward, I would harness that air and squeeze it, I would build a certain amount of pressure. What if I didn't close the intake valve until my piston got to here? What would happen to pressure? It'd be less, right? That's why we'd have low compression. When we have a late intake cam, we have low compression. An intake cam drastically affects compression in the cylinder for that reason. If we close it early, we build more compression. If we close it late, we build less compression. An exhaust cam really doesn't affect compression at all. I can think of one scenario, and we'll go over that in a little bit, but think about it. Where the exhaust cam opens or exhaust valve opens or closes will only really affect what's inside the cylinder. Exhaust charge or more fresh air fuel charge. That makes sense, but it won't change the compression except for one condition. We'll cover that.
So what you're saying there is basically in the syringe analogy, you're pushing the plunger in the syringe is going up before you're putting your finger over.
That's exactly it. Instead of closing that intake, put my thumb on the end when I can take full of...
The ultimate pressure you can make is less.
That's exactly it. Due to less volume.
To start before you
Exactly.
start pressure.
That's exactly it. And that's why I tie it to a syringe analogy, because you could picture the syringe in your mind, right? Mm-hmm. It's hard to picture what happens inside a cylinder because it's not very comfortable sitting in that combustion chamber. I could fit in there. You probably couldn't. So... Straight towers and even but it makes sense, doesn't it?
Yeah.
It's a lot easier to think of it like that. Why would I have straight towers and even pockets? No leakage, right? The cylinder still seals. Late exhaust valve opening, late intake valve opening, late intake valve closing. Why were those late? Cam's late. Simple as that. Okay, here's an example. This is an in-cylinder waveform with advanced cam timing. Again, single overhead cam. Intake and exhaust are both affected. Let's cover this. Straight towers. Why? Nothing's leaking, right? Uneven pockets. Now wait a minute. We talked about the syringe. If we had a leak, we'd have this pocket go way deeper, right? Let's talk about that for a minute. That one appears to be higher than the other one, doesn't it? Let's talk about that for a second. If I had my syringe in my hand here, okay? And I had it fully stroked. If I would normally push it up a little bit and then close the intake valve, right? And trap a charge in there. If I came back down, back to where I started, but I took my thumb off early, could I pull the same vacuum I started with? I couldn't, could I?
Suck exhaust back there.
Right, well, not at this point. If I started with my syringe, let me start over again. If I had my syringe and I had it fully extended, I put my thumb over the end and I pushed it up on compression and I came back down. If I normally came back down to here, I'd be back where I started, right? What if I took my thumb off before I got all the way back down? I couldn't pull down to that level I was at, could I? That's what that is. That's because the exhaust valve left the seat early. Why? Because we have an advanced cam. Does that make sense?
But enabled, instead of pulling the vacuum, it enabled to get the exhaust.
The exhaust valve opened early.
And so, instead of pulling intake, it can pull from the other side.
Yeah, the piston is still descending while that exhaust valve opened, correct. So that cylinder is exposed to the exhaust stream. But the significance of this capture, this pocket is leaving, the pocket is not coming down as deep because it's like we took our thumb off the syringe early before we got down to a full stroke. So that's why we have uneven pockets. That's why that pocket's more elevated. If it was cylinder leakage, the pocket would be lower, wouldn't it? It'd be beneath the intake pocket. Early exhaust valve opening. Early peak vacuum for the same reason. It's an advanced cam. The exhaust closes early. The intake intake opens early. So our intake vacuum pocket is going to be shifted to the right as well. Excuse me, to the left as well. And of course, early intake valve closing, right? This closes early. So what happens to the volume inside that syringe if we close the intake valve early? We trap more air inside it. What will happen to compression? It'll go up. Exactly. You're getting it. Here's an in-cylinder waveform. Again, we're running. This has a late exhaust cam. Now this is a dual overhead cam setup. Meaning what? Intake and exhaust are what? Separate, right? So we only have an issue on the exhaust side. The exhaust side is shifted late. The intake is just fine. So let's go through this. High running compression. The first engine that comes to mind when I think of this scenario, a twin cam engine with an exhaust cam that's late. 4200 series Trailblazer. Picture that motor in your mind. If I have an exhaust valve that's late, we know what valve overlap is, don't we? When the intake valve and the exhaust valve are open at the same time. Overlap's supposed to be for a certain amount of time or duration, right? If I hold that exhaust valve open longer because the exhaust cam is late, doesn't that make duration increase? Meaning the cylinder inhales more gas, almost like the EGR effect, right? What if those gases are really, really, really hot, like you were beating the snot out of this engine when this phaser got stuck? Doesn't hot gases take up more space than cold gases? Couldn't that boost compression a bit? So it's not going to do it all the time. If the engine's really hot, you could potentially have an increase in compression. Remember I said earlier, exhaust valve timing really doesn't have much to do with compression at all, just the density in the cylinder, except in this scenario. Unless your exhaust cam was off 180 degrees, then it could affect compression, right? If it was open when the piston was trying to go up on compression. That's the only time. But if it was anywhere over in here, it's not going to affect compression. If it was retarded or advanced 180 degrees, it could. Does that make sense? Straight towers. Why are they straight? We don't have much leakage at all. We actually don't have any leakage. Late exhaust valve opening for obvious reasons. We have a late cam. This exhaust valve, this exhaust ramp isn't changing directions over here at 30 or 60 or 45 degrees. It's darn near bottom dead center, isn't it? Before the exhaust valve actually opened. You see the red line? Here's top dead center. Here's bottom dead center of the expansion stroke. The exhaust valve typically opens about here. But that change in direction is occurring right here. That's when the exhaust valve is opening, right? When this pressure changes directions here. You guys see that? So it's shifted to the right because it's late. Normal intake valve open, normal intake valve closing. Why is that? Dual overhead cam. Only exhaust valve exhaust cams are one affected. I want to point something out here. This area over here where the exhaust valve is still open and the intake valve just open, also known as overlap. You see how it doesn't pop straight down, does it? Why? Because the piston, the intake manifold for a little bit longer is being exposed to that exhaust manifold and the vacuum is suffering. That's why that doesn't pull straight down. This is the one occasion when you can see the exhaust valve close. And you see that little bump there? As soon as the exhaust valve closes, boom, then vacuum drops. Make sense? And again, elevated peak vacuum, we can't pull the vacuum down because the exhaust valve was open. Pocket differential depends. I had people I was helping out on Facebook, some of the Facebook chat groups. I enjoy doing that. It's a lot of fun for me. I don't have a lot of time anymore to do it, but I really enjoyed it when I did have time. And I remember distinctly, I don't remember who it was, it doesn't matter, but somebody had misdiagnosed an engine as being bad. And they boasted about it on Facebook. And when I looked at the waveform, immediately I saw that the engine wasn't bad. It was simply a late cam. And what happened is this cam, this exhaust valve opened so late, as this piston came all the way down to bottom dead center. Remember, we closed this intake valve about 60 degrees after bottom dead center, right? We opened the exhaust valve about 45, 50, 60 degrees before bottom dead center. If we open this way late, we've got another 15 degrees of crankshaft rotation for that piston to come down. That's the same as having a little bit of leakage. It's going to pull this pocket way, 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 way down. When the valve finally opens, it's going to disappear. But to the guy analyzing the waveforms, he didn't have enough experience, and he thought it was excessive cylinder leakage. So he sold the shop an engine. I don't know if the engine actually got replaced, but I private messaged him to tell him that it was an oversight, and he really has to start throwing his cursors down. He kind of, shot from the hip. He didn't analyze the waveform. He saw what it looked like and immediately called an engine. Huge mistake.
Could you go back one, Brandon? I really want to get the one before this.
This one right here?
The advance for the stock, yeah.
Okay. What's your question?
High compression. I'm not I know it happens, but I'm not visualizing why the advance gives the higher
Okay.
compression. Because
Let's go back to this syringe.
I understood the low because you're starting late. So in my mind, I'm thinking the high is because you're starting early, but you're still working with the same size syringe. So
Okay.
how does it?
Let me explain it to you like this. First of all, I'm going to tell you, if you recall from the beginning of the class, we typically don't close the intake valve until about 60 degrees after bottom dead center. 60 degrees after that piston starts heading up. Okay?
Okay, so it's got,
Right.
a better word, it's got free or unsealed travel.
Exactly.
Okay.
So if this is my syringe stroke here, okay, let's use this line right here. If this is my entire piston stroke, if we don't normally close the intake valve to here, about that much charge is gone before we close it. We can only squeeze this much volume. If I close the intake valve early, we close it here.
I got it now.
Make sense now?
Yeah, because I was basing and not thinking about the lost again track of when the valve was closing. I think if, my thing was saying, well, if it's closing at 0,
Right.
I
Yes.
understood it, the high or the low compression.
Right.
But then now that we're talking about when you're losing
Exactly.
sealed travel time.
Exactly.
That's how I'm wording
The piston didn't
it. And
capitalize.
then you're gaining sealed.
Exactly.
You're not working off of 0.
You're right. You can basically say the stroke of the piston,
Yeah.
that entire stroke, they weren't capitalizing on the entire amount of contents potentially fill.
Potential.
Right.
that-
We push some of it out before we close the cylinder.
But the potential is a
You got it.
X factor. It's
Exactly.
correct. It can't
No,
be more
you-
than it's capable of.
You got it now.
Okay.
So I think we got past this.
Yep.
And the pocket differential, again, if you're way late on an exhaust cam, way late, it could pull the pocket down. But you guys understand why? Because we close the intake valve here. We're supposed to open the exhaust valve here when they're at the same level. If we wait to open that exhaust valve, we still got another 15 or 20 or 30 degrees before we get to that piston that syringe can keep drawing down. Does that make sense? That's why we pull that deep pocket. Okay, here's an in-cylinder waveform with late intake cam. Again, only the intake camshaft. This is a twin cam. So for the same reason we just discussed there, I forgot your name, I'm sorry.
Bear.
Bear?
Yep.
Like grizzly bear? Okay.
Teddy, grizzly, whatever.
Teddy bear, there you go. For the same reason, we would have, for the same reason right here, we have low, man, that's really hard to see with this light. Can you see that at all, Jim?
Turn that light switch off.
This one here?
Yeah.
Oh,
Is that better?
yeah.
Can you see me okay?
That's better.
Okay.
You look like a dog guy, but you're in the dog.
Picture, yeah.
So anyhow, we normally close the intake valve about 60 degrees after bottom dead center. But now we're way late. We're shifted closer to 90 degrees. So some of the contents are being pushed back into the intake manifold before that intake valve finally closes.
Before you start compressing.
So since there's less volume in there, it's like lowering the compression ratio, right? That's exactly what's happening. So that's why we have low compression. The leaning towers. This one's going to be a tough concept to grab, but stick with me here. Let's pretend this is a 4-cylinder engine. Actually, it is a 4-cylinder engine. Meaning each cylinder has the same cam, okay? We understand the cam's late and why it affects this cylinder, but we want to talk about leaning towers. Leaning tower signifies we build pressure at a different rate than we lose pressure. The piston comes up, we build pressure, and all of a sudden we lose pressure. I want you to think about cranking cadence. What happens when you have a cylinder that lost some of its charge, a significant amount of charge? What does the cranking cadence sound like on that cylinder when you're cranking the starter over? Okay? Picture all 4 cylinders doing that. You start to squeeze, you build low compression. On a 4-cylinder engine, you got one up at 180 degrees away from the other one, right? They do this. So one's on the intake stroke when this one goes up on its compression stroke. When this one's coming down, the other one's going up on compression. That starter, or that crankshaft's going to speed up again. So it's going to yank this one down real fast. Does that make sense? That's why the towers lean like that. And again, the exhaust valve is on time here. Why? Because we only have a late intake cam, and this is a twin cam. We have 2 separate cams for each set of valves. Uneven pockets. Again, if we close that valve late, if this was the stroke of our engine, the stroke of our combustion chamber here, and we normally close the intake valve here, but since this is late, we close it here. We squeeze this much, but then we pull the piston all the way down before the EVO happens, right? That's why we build that pocket there. Does that make sense? Okay. So again, normal exhaust valve opening here. This one looks to be at about 30, which is normal for this engine. But again, late intake valve opening and closing because our late intake cam. And you can see right here the effects. You see that little dip right there? Here's bottom dead center, top dead center. That's where the intake valve is supposed to be opening approximately. It's not opening to here. Think about this for a second. We get to top dead center. Let me get out of this light. We get to top dead center. The stroke of the plunger's all the way up. At that point, to open the intake valve and inhale a bunch of air. The exhaust valve's already closed, isn't it? Right? But what if I open the intake valve late? Don't I pull that piston down against closed valves?
Yeah.
Don't I pull that cylinder into a vacuum because I'm trying to make the area bigger? I am making the area bigger, but I'm not letting any air in. So it goes into a state of vacuum. When does the vacuum disappear? When what finally does open?
Intake.
That's what that is. We start to pull a vacuum here. See that? Can you zoom on that, G? Actually, I can zoom. How about that? Better? We start to pull a vacuum here. Why? Because the piston's coming down against closed valves. Right here is the point where the intake valve opened. Not here. It's supposed to open here. Here's where it opened, and it let that vacuum out of the cylinder. Does that make sense? It opened late, and then it closed late. It's supposed to close here, but it didn't close till here because the whole cam shifted to the right. Does that make sense? Okay. Let's do a little case study here. This is to reflect insufficient valve clearance. Now I want to show you something here. This vehicle came into the shop with a rough idle, almost like a misfire. Okay? I will tell you these valves were just messed with. There was a recall on this car. The car came in. Those of you guys remember the Honda Fits when they had that recall in the valve train a few years back? You remember that? I was involved in a few of those repairs. I was in a dealership at that time. And we were supposed to disassemble the rocker assemblies if they fell within a certain date and replace these devices called lost motion springs. It's just part of the valve train. And then when we put it back together, we're supposed to do a valve adjustment. Well, what happened was the guy that was working on this car, he botched the valve adjustment. He didn't have a good feel for it, and he over-tightened the valves. So this thing came to me, and it was running rough. And I decided to go in cylinder. Rather than pull the valve cover and check all the valves first, I wanted to make sure I was going to find a valve problem before I went into the engine. Every test I do is to not fix the car. It's to justify the next test, the test that's going to bring me closer and closer to the fault. Does that make sense? I used to shoot from the hip. It's not fun. Now it's a lot more fun to do little tests that are easy, to give me a lot of information for a little bit amount of time, and then leads me towards going, in this case, into cylinder, underneath the valve cover and checking for valve problem. So idle really rough. My preliminary testing led me to this. Again, I didn't just pull this in my bay and start pulling things apart. I had tests that led me to this point. So I went in cylinder, and this was an old snap-on motor, so the technology wasn't there. That is here now with our PC-based lab scopes. You had to jump through a few hoops. I saved this waveform through a thumb drive, and I stuck it on my computer, and I blew it up in a paint program to get a better look at it. okay? So we zoom in on it. So I want to show you something here. Forget about valve specs. I didn't ask you guys to open up a manual and say, when's the valve supposed to open on a Honda, did I? But what am I asking you here? What looks weird about those pockets? Do they look to be of the same depth? Use the green line as a point of reference. No. What's higher, the left side or the right side? The left side, it's elevated. We talked about that. If an exhaust valve is tight, what happens to duration? Stretches, right? Meaning it opens earlier because it's closer to the valve and it closes later. Well, if I open an exhaust valve earlier, remember we talking about, we take the syringe, we push it up. If we pull it down to the same spot, we should be at the same pressure levels we started with. But if I take my finger off the syringe before I get back to the full stroke, we lose that vacuum. That's what's happening there. So right there, this is inferring we have a valve that's occurring early. Pierre pointed out yesterday that this isn't a nice sharp transition here. It kind of gets a little bumpy here. It goes like this, then it changes directions, and then it changes directions. Another indicator that a valve is tight. But also come over here on the intake side. This isn't happening over here like top dead center. It's closer to like, that's 30. So that's like 15 degrees before top dead center. It's a bit early. So this is about 45 degrees. I don't know if that's good or bad. I don't care about the numbers. I'm looking at the shape of the waveform. But I am going to write down that number and see if I can make a change. So right now, looking at this, I'm assuming I can see I have a tight exhaust valve, and it looks like I have a tight intake valve. What does that do to duration? Both of those increase duration, doesn't it? If I increase duration, I increase the time when both the intake and the exhaust valves are open. Meaning when I go down on the induction stroke, I'm not only sucking fresh air, aren't I? I'm sucking some exhaust gas back in that cylinder too. What do you think that does to the density of the charge inside that cylinder? It pushes all those fuel molecules and everything out of the way. Why? Because exhaust gas is inert. It doesn't do anything. It just takes up space. Okay, so it's going to affect the combustion process and cause that cylinder to run rough, maybe even misfire. So that's what I see here. So now it's time to go in the cylinder. So again, just to recap on these points of interest I see, we've got uneven pocket differential. That's clear as crystal. It indicates the exhaust valve left its seat early and vented the cylinder early. Intake valve opening appears early as well. So this is about 45 degrees before, and this is 15 degrees before. This justifies the need for valve inspection. Again, now I have a reason to open up that valve cover. I used to go to work with a knot in my stomach because you never know how the day's going to go. You know what I mean? But when this kind of testing technique and having an understanding of what this scope's showing me here gives me confidence. Your confidence goes through the roof. You feel like putting on your cape in the morning before you go to work because you really do have that confidence. It makes work fun again. Uh-oh, what do I got to do? There we go.
Reboot.
We did that already. Oh, crap.
Switch slides, quick.
Okay. Is that what it was? It just...
I don't know.
Okay, so anyhow, so we go in there. Here's a zoom of it afterwards. I adjusted the valves. We were at 45 degrees before, now we're closer to 30. We were at like 15 degrees before, now we're closer to like 10 or maybe even 5 or 0. We're close, but more importantly, look at the pockets. They're about even now. How do you think this car ran when this was done with this valve adjustment? Smooth. Why? Because we got rid of the overlap. And now it had more fresh air in there. We need EGR. We need that overlap to help scavenge the cylinder. But if there's too much, it's going to interrupt, it's going to disrupt the combustion process.
Just for a reference, would that be extremely tight or marginally tight?
My definition of
I mean, not in thousands, but just out of curiosity to make that, you know.
you would, it had almost no clearance. Okay. So if specification was 10 thousandths on that valve, maybe I couldn't tell you what it was, but
almost nothing.
But an engineer's not going to design it to open up and create too much overlap at idle. That's the point.
Right.
They offer you a spec so you can adjust that. That's something you can associate with distance. What they're really talking about is how much overlap they want to give that
Right.
engine cycle.
Brandon,
Yes.
comment.
Please.
Well, just look for low map voltage on a B or D series Honda.
That's a great point. Typical
Yep.
Hondas, if you're referring to map voltage, 0.85 to 0.95 volts is typical what you see. When valves get too tight, you start to relieve some of that manifold vacuum and your map voltage goes higher than 0.95. If the valves are too loose overall, you're going to have lower manifolds because you have less overlap. It's going to put more of an effective pull on that manifold. Problem is, what if I have one cylinder with a tight valve, like this case? How much is that going to affect your map overall? So you have a point, yes, loose valves, tight valves will affect map, but when you have one cylinder with a problem, it's not likely to affect it as much. Okay, just keep that in mind. The manifold, the bigger the manifold, the more of a buffer you have. So the smaller the manifold, the more of an effect that's going to be, if that makes sense. So we adjusted the valves, we got rid of the excessive overlap, the new waveform was acquired, the pockets are now even, IVL more defined, both valve events, both the exhaust and the intake occur earlier. Here's them side by side. Can you see the difference there? We were at minus 45, now we're at minus 30. When I say minus, I mean before bottom dead center. We're now at minus 15, now we're close to, I wrote 10 here, but looking at it now, it looks closer to 0. So we've drastically improved the breathability of this cylinder. And now their misfire or symptom went away. So I got this next case study here. Now this was a fun one. The car came in. I'm going to present it to you guys how I received the vehicle. The car came in with a MIO and a PO 341 indicating incorrect camshaft to crankshaft correlation, which kind of infers a potential timing issue in the eyes of the PCM. I heard noise in the valve train, and it changed with RPM. The clickety-clack noisy you hear from underneath a valve cover when an engine's like poorly maintained. That's what it exhibited. This thing had 162,000 miles on it, and there was like not a drop of oil on the dipstick. And this car was a real turd, pardon the expression. I mean, I actually put gloves on to get in the car. Not to prevent the car from getting dirty, but prevent the car from getting on me. Now, I'm serious. I spoke with this lady, and I asked her when the last time she had the valve adjustment done because I wanted to know, am I going inside this engine or not? And she never even heard of a valve adjustment. So it's highly likely these valves are at least 60 to maybe 60,000 miles overdue for a clearance inspection. So knowing that, and the noise, and the fact that there's no oil on the stick, there's a good potential that I got to adjust the valves in this car. So I want to ask you guys a question. Sitting in these seats right now, if this car came into your shop, do you have ammo to go in there and approach the customer and say, we really need to check the clearance on these valves before we go any further? I think we do, except if you have these tools and techniques. Since I know how to do this stuff and I'm comfortable with it, and it'll take me a few moments to pull a spark plug out, I might be able to see something that would tell me for sure if I have a valve issue or not.
Well, I mean, better yet, to show the proof of your repair afterwards, too.
Exactly that. Exactly that.
The printed picture.
The printed picture. So let's think about that for a moment. Can I see valve clearance issues through the eyes of the lab scope and the pressure transducer and spark plug hole? Directly affects overlap, doesn't it? We should be able to see that. So if anybody knows this answer, don't scream the answer out loud. I don't want to know what you think is wrong with the car. What I do want you to point out to me is regarding pressure over time, what are you seeing regarding pressure over time? What's happening in this waveform, this running compression waveform that looks strange to you? What looks different about this waveform than what you know to be a good waveform from what it should?
Peak at 360.
So you got a peak at 360. So if this is pressure and this is time or degrees per crankshaft rotation, what happens at the 360 mark to pressure?
It's increasing.
Pressure is increasing. This is the compression stroke. This is the expansion stroke. This is the exhaust stroke. What that says is, as we get closer to the top of the exhaust stroke, pressure starts to build. What valve is supposed to be open on the exhaust stroke? The exhaust valve. So, should we be building any kind of pressure in the cylinder when the exhaust valve is open? We should not. So, said another way, what had to happen right, not here, but what had to happen right here for pressure to start to build? The exhaust valve had to close, right? It had to build pressure in the cylinder. Now, I know I don't have any numbers here, but this is probably 10 or 20 psi here that just happened in the last maybe 45 degrees of crankshaft rotation before we got to top dead center here. So we got pressure building in the cylinder. We agree the exhaust valve had to close, right? Okay, so let's back up a second. Clickety-clack, clickety-clack, clickety-clack. We're suspecting loose exhaust valves. Loose valve clearance. If we have loose valve clearance, what happens to duration? Gets shorter, right? The valve opens later, but it closes earlier. Closes earlier. If it closed early, couldn't we trap some air in the cylinder before the piston got to top dead center? And if it did, if that continued if that piston continued to move and the area got smaller, wouldn't pressure had to go up? So we could have loose valves here, right? Let's back up a second. P0341, remember?
I'm not seeing that, I'm not putting that here, I can't get it.
All right, say that again. That's okay. We can clear this up quick. What's your question?
I don't understand how it was set at 341, you know, I mean.
Oh, okay.
341 is a direct.
So P0341. That's, remember, we got to use all the clues, right? We don't have tunnel vision anymore. No offense, we're not dealership guys. We're independent technicians, and we have to know how things work, not how Hondas work, or, you know what I mean? So we don't have tunnel vision. We're going to broaden our horizons. We're going to gather all the data to make some diagnostic decisions. And one piece of data says, P0341, that the computer's not happy with where the crank signal and the cam signals fall relative to each other, inferring a what? A cam timing issue. So now I have a dilemma. Do I approach my customer and say, we got to adjust the valves because I hear it and I see this? How am I going to tell if I have a cam timing issue? What if the exhaust cam, first of all, when a chain stretches, and the cam jumps, timing jumps to the retarded side, typically, right? Your crankshaft oversteps the chain, which makes the cams late, right? There's a possibility, on a rare occasion, it could jump advanced. That typically happens when somebody's in the engine and they don't do something right. But on occasion, it does happen. So just for the sake of argument, if the exhaust camshaft became advanced and things happened early, is there a potential I could close the exhaust valve early because of that and create the same scenario? There is. So how am I going to tell the difference in this capture whether I have loose exhaust valve creating this problem or jumped advanced early exhaust cam?
I think the exhaust valve opens.
You got, what's your name, buddy?
Eric.
Eric just said it right there. Do you hear what he said? He said you have to look at where the exhaust valve opens. Watch my hands. You guys know, like, the hump for duration, where a cam opens and then, or a valve opens and a valve closes? Let's call this normal duration. If I tighten an exhaust valve, if I tighten it, any valve, does it open earlier or open later? It opens earlier. Does it close earlier or does it close later? Look at duration. It went up. If I loosen it, it opens late and it closes early, right? Duration changes with valve clearance. If I jump, now watch my hands, if I jump cam timing, so it's going to move on the left and the right equally, isn't it? So what Eric was pointing out is, this tells us the valve closed early. This will tell us on this side, the combination of the two, whether the cam shifted or not. Now I know there's no smaller, more resolute cursors here, but we can do some math. If this here is 180, half of that's 90, half of that's 45. We're like 60 degrees before bottom dead center. We're early here, we're early here. Are we pulling the front cover off or are we pulling the valve cover off?
Front cover.
The front cover. We're going to sell her timing components. I'm going to sell her a valve adjustment too, right? You're going to pull them off. Oh, you'd be surprised, Pierre. No, I'm just kidding. Pierre said you're going to pull them both off anyway. I've seen guys do some sneaky stuff. Anyhow, we're not only going to sell her a valve adjustment. We're not going to have that conversation, you know, Mr. or Mrs. Customer, we had to adjust your valves first. Son of a gun.
5 minutes to break anyway.
Okay. I'll be done with this in 2 minutes. Bear with me.
Valve adjustment.
Yeah.
Okay. There we
Hit your
go.
computer keyboard.
Is that what it is? All right. So, I'm not going to have that conversation with the customer where, you know, we had to adjust your valve first just to be sure. You know what I mean? I don't want to say we got to go spend $200 of your money and then I got to come back and tell her, now you need a timing chain. Because I have these tools and these techniques and the ability to test this in this manner, I feel like I have the responsibility. And I'm not preaching to you guys. This is just my outlook on it. There's a much easier way, and this is it. So she's going to get her valve adjustment, and she's going to get her timing components replaced. But guess what? If she decided she didn't want to do either then, how much time do I have invested in this? Do I have to walk up to her, wiping my elbows off and getting the oil off, only to find out she's angry, she wants to go home right now, and she doesn't want to spend any money? Now you're putting this thing all back together again, right? It's a big waste of time. But to go in there through the eyes through the spark plug hole and through the eyes of the lab scope and the pressure transducer, we can see this stuff. This is our crystal ball diagnostics. Does that make sense? So we had justification to pull it apart, but more importantly, let's cover what we see here. Even pockets, almost. This is a bit early. You could see this one leaving the seat earlier, right? I wrote even pockets there. I think I'm going to change that. This one is leaving the seat earlier. If I drop a horizontal cursor here, we would see that occurring early. Straight towers, there's no leakage. Defined valve events, right? We can see the valves open and we can see the valves closing. Timing's the issue here. We pulled the front cover off. That plunger on that tensioner is fully extended. It can't go any further, and the chain suffered. It stretched, and that was the clickety-clack. It wasn't the valves making the noise, it was the chain. Valves needed adjustment, but what we were hearing was the chain. So again, what we found, the large spike at the top of the exhaust stroke indicates pressure building. The intake valve events appear to occur as expected. This suggested the exhaust valve is closing early. A loose exhaust valve will open late and close early, meaning low duration. Early EVO, early EVC points corroborates an advanced cam and not lose valve clearance. So the strange cranking cadence and a constant miss... Oh, this is a different one. Let's wait. You want to take a 5-minute break, you said, Jay?
Yep,
Okay.
let's break.
We'll be back. Guys, welcome back. We just started off, we finished off with the beginning of this case study here. Now, I like to teach a little bit differently than a lot of people, and for good reason, especially with pressure waveform analysis. I want to give you the answer, you know, the end result up front, so you don't have to try to guess why we're going through this. In this case here, the intake valve is not going to be opening. So listen to what I just told you and how it's going to reflect in a series of events that come up here. So this car was in the work bay, in another tech's work bay when I worked at the Honda dealer. And the car exhibited a strange cranking cadence. It had a constant misfire once it did start, and had a check engine light on with a P0302 indicating cylinder number 2 is misfiring. Now the tech that was working on this car, his analytical skills were not the greatest, but he did what he knew how to do, so he started playing swaptronics. So he swapped coils, and you know, sometimes we're limited on what we know and the tools we have, and he tried to make the best of a bad situation. So he did all he knew how to do, and he swapped the coils, and that's easy enough. You know, that didn't kill too much time. It was pretty smart, but by swapping the coils, nothing happened. So then he replaced the spark plug for that cylinder, and the misfire prevailed. But things got a little bit weird is when he pulled the intake manifold off and then pulled the fuel rail out, and he swapped the injectors around and put the car back together, only to find out that the misfire is not only still there, it's in the same spot. At that point, he decided it was best to start testing for compression. That's where he lost me. So the results of his compression test with his mechanical gauge revealed 25 psi of compression. In your mind, before what we discussed tonight, what does 25 psi mean to you? What's wrong with that cylinder?
It's not a Honda, right?
It's not leaking. I mean, it's not sealing. That's what our mind tells us because that's what the compression gauge tells us. Low compression means that there's not enough charge in there. Couldn't get anything in it, right? In this case, we know that. But if we didn't know that, if we only knew our gauge and we weren't thinking about volume, we were just thinking about a cylinder's ability to squeeze, having 25 psi in it would probably tell most of us, oh my God, we got a cylinder leakage issue. Problem is, he did his cylinder leak down test, and he only had 2% leakage, which is not what we'd expect to correlate with a compression reading of 25 psi. So he calls me over. Oh, knowing who it was, the first thing I did was look in the hose to make sure he took the Schrader valve out, right? So he did. He did the test properly, and it indeed was only leaking down 2%. But he couldn't wrap his head around how could I have low compression and no leakage. So that's when I came over with my lab scope and my pressure transducer. And in quite literally 5 seconds, I threaded this thing. Actually, I left this hose in there. I put my pressure transducer on it and said, John, start the car. This thing no sooner ran for 5 seconds, and I knew immediately what had happened. This picture came up here. Now, we talked about smooth transitions and sharp transitions and the relevance behind both of those, but first let's go through this waveform. Peak compression here is registering only 10 psi. But remember, what did I say about the snap-on characteristics? That they offset. Once you get the car started, they offset about 10 psi. It's just a trait of that scope. It's something that you just have to learn to look past. So what we did was I see the top of the exhaust stroke is exhaust plateau is about minus 10 psi, which we know it's always going to be above atmospheric pressure. So what I did was if I add 10 psi to that brings me to 0, which means I got to add 10 psi everywhere. So now my scope's reading closer to 22 psi. Okay, not that the numbers matter. We're not looking at numbers here. I'm just telling you overcoming one of those pitfalls of this scope. we're analyzing the way the trace is laid on the screen. So what we see here, do we see even pockets and straight towers? We do, right? What does that mean about the cylinder's ability to seal?
That's good.
It's not leaking, and our cylinder leak down test confirms that. But right when we get to bottom dead center, we see a real sharp rise in pressure, right? Indicating what happened right here. Exhaust valve open, and then we get over here to top dead center of the exhaust stroke, and our intake valve that's supposed to open here would yield us a ramp that goes almost straight down, wouldn't it? Does that look like it's going straight down? It doesn't. We already know the intake valve's not opening, right? But I want to ask a question. Why do I still have 20 inches of mercury here if the intake valve never opened?
Because you've got the same, what you were talking about before, where the intake valve would
Go ahead, you got it.
normally open. You've got that extra, what Bear was asking before, that extra.
Tell me with the syringe. What happens with the syringe in this scenario? Where's your thumb?
You're never taking your thumb off.
Went back to where it's.
Thank you. Exactly. Now you're getting it.
Delta.
The plunger is being pulled down in my syringe, but I didn't let any air in, did I? Because the exhaust valve's already closed. The intake valve never opened. Matter of fact, pressure is changing. You see that rate of change is the same, right? It's coming down as the piston goes down, and it starts to go up. Where do you think bottom dead center is? Right about here, wouldn't you say? It's round because the area in the cylinder is getting bigger, and pressure's coming down, and then the piston changes directions, doesn't it? And then the area gets smaller and pressure starts to rise. That rounding is very undesirable, and that is what I was looking for. The moment I started this car, I recognized it as an intake valve not opening. Instantly. Isn't that real easy to see once you know what to look for? But it explains the whole scenario. Low peak compression because the cylinder couldn't fill. Why? Because the intake valve didn't open. Straight towers and even pockets. Why? Because nothing leaked out. It seals just fine. Defined exhaust valve opening because there's nothing wrong with the exhaust valve, but the rounded intake pocket indicates the intake valve never opened and explains why everything else appeared as it did. Does that make sense? And the round pocket, once again, points to no intake valve opening and no intake valve closing.
What did it do, spit a rocker?
That's exactly it. What I did to this guy working on this car, I told him in 5 seconds I had this car diagnosed. I had enough confidence to tell him you have to take this intake manifold back off, you have to take the coils out, you have to pull the harness off the back head, you have to take the rear rocker cover off, and then before you do all that, make sure they have a rocker assembly in stock for cylinder number 2 intake side because your VTEC pin came out. And that's exactly what happened. It lost its ability to link the primary and secondary rocker. I don't want to get into Honda systems, but they have the ability to disable cylinders. Chevy calls that active cylinder management. Chrysler calls it displacement on the van. Honda calls that variable cylinder management.
I'm assuming it's a 3.5 V6.
This is the 3.5 V6. This was in a Honda Odyssey. So, not that I'm trying to get into the Honda side of things, but I'm saying because I know how the vehicle's made, it can explain why this happened. And I knew exactly what he was going to find when he took it apart. But I had the confidence to tell him pull it apart. I had no doubts at all. So to recap, the results of the analysis indicated a lack of intake valve opening. The results justified disassembly and inspection. That's the takeaway from this whole thing. It gave me the confidence to move forward. Valve cover was, number 2 was, bank 2 valve cover was removed, bank 1 rather. The intake valve rocker for cylinder number 2 was not functioning. The VTEC, variable cylinder management pin, had displaced and failed to actuate the intake valve. Okay, if I lost anybody on that one, please respond to G and he'll get any questions over to me. Let's move on to the next case study. This is a waveform involving I'll call this a case study involving a restricted catalytic converter. Again, I like to tell you guys what's wrong with the car first, and you can help me put the puzzle pieces together. So this vehicle exhibited a decent idle quality, but it did have a P0420 stored. The vehicle failed to accelerate. It performed very poorly. It had no power. This is a vehicle of an in-cylinder four-cylinder engine of a speed density fueling strategy. Let's talk about the significance of a speed density system. In order to calculate how much fuel gets to the cylinders to provide the proper air-fuel ratio, we have to know how much air is coming in. Getting the fuel there is very easy to do. The engineers designed every aspect of that fueling system. But it's physics that determines how much air gets in. So we have to properly weigh the air, and we can do that with a mass airflow strategy that directly measures the air, or we can do it by way of speed density, which we look at pressure differential between what's inside the intake manifold and the pressure in the atmosphere out here. And if we know the temperature of the air, right, and the temperature of the engine, we can infer how dense the air is, meaning how much we can squash into a given area. And if we know how fast the engine's turning and that it only inhales every other stroke, we can in fact determine how much air is in that engine and then match the fuel to it, right? Speed density works phenomenal. It's very reliable. In fact, some of the newer design fueling systems use a map sensor. They use a speed density strategy. That's how reliable it is. The problem is, when something affects engine breathability and pressures get screwed up, that's when it falls flat on its face. So we got to keep that in mind as we move forward. So I'm going to grab some, I call it low-hanging fruit, some easy-to-grab information so I can help lead me down a diagnostic path. So I always refer to my scan tool PIDs because that's diagnostics from the driver's seat. And my map signal voltage was very elevated. Let's think about that. Pistons displace air, and engine's an air pump. So when a piston inhales, if all 4 or all 6 or all 8 or all 10 cylinders are trying to inhale more air than the throttle plate's willing to allow, we're going to evacuate that intake manifold, aren't we? And we're going to draw it into a vacuum. And if our map sensor is referencing the intake manifold, it's going to output a signal that infers vacuum, right? Low pressure. So if I can't, I said an engine's an air pump. If I can't breathe, if I can't exhale, I can't inhale. You guys ever try breathing in a 2-liter soda bottle? You know, once you use up the oxygen in air, it's very hard to breathe. If I can't get the air out of the cylinders, I can't get fresh air in. And if I can't get fresh air in, I'm certainly not going to draw the intake manifold into a vacuum, are I? Am I? Excuse me. So the map signal voltage is not going to reflect deep vacuum. It's going to reflect low vacuum, otherwise stated load. So when the PCM sees load, what does it do? What does it do to fuel injectors? It widens the pulse width to deliver more fuel, right? Of course, we know that fuel is unnecessary. So through the eyes of the feedback system, through the air-fuel ratio sensors, the oxygen sensors, what happens to fuel trim? It should go very negative. We got to think like this. We got to know our opponent. We have to understand that this is a speed density system, and if this was a mass airflow system, our fuel trims would be totally different. I have a different approach, wouldn't I? You have to understand what you're working on. It's very important. So my fuel trims were heavily negated at all times and hovered around 25%. So right now, we know this car can't, putting all these puzzle pieces together, we know this car's not breathing very good, is it? So in-cylinder analysis will quickly determine timing or restriction. What can I do if I didn't have pressure transducers and a lab scope? You know, we can cut the exhaust system, we can pull the oxygen sensors out of the pipe to get rid of a potential restricted area, right? Bypass the restriction.
Back pressure test.
Back pressure test. The only problem is this. We can even look at a vacuum gauge. Every time I take an O2 sensor out of an exhaust system and I didn't sell it, I pulled the threads out. Every time. If I sold it, I wouldn't have a problem. But because I didn't sell it ahead of time, that's when the thread comes out and then my boss gets mad at me. It happens every time. I won't mention names, but I know somebody, very reputable shop owner, had pulled a O2 sensor out of an exhaust system, and the hot gases were blowing up on the floor, and he melted the carpet of a minivan. So you got to watch those things. They talk about vacuum gauges. We can look at the vacuum gauge for the same reason we look at a map sensor. But the problem is when you start getting back pressure, that gauge is going like that. It's very hard to determine. Unless this thing's plugged rock solid and there's no airflow, your vacuum's going to suffer and you're going to see it. But when it's partially restricted, it's going to be going crazy. Same with a back pressure gauge. I've seen it 100 times. So now I got to determine all those symptoms I have, the poor power, the poor fuel trim, right? Excessive fuel. I could have a timing issue. I might also have a CAT code, right? But I could have a timing issue for sure, especially if the car had a jump timing on a cam that's not monitored with a cam sensor, right? So that could cause low vacuum, but I could also have an exhaust restriction. So the best way to determine this, the fastest way by far, is to pull a spark plug out and view back pressure in the exhaust system through the eyes of a pressure transducer and a lab scope threaded into a spark plug hole. So check this out. In engines and air pump, okay, we're talking about restrictions. If you could picture right here a water spigot coming out of the side of this wall here, and if I put my thumb over the hole of that water spigot and covered 90% of it, but I left a little opening at the bottom, if I crack that spigot open off its seat a little bit, let some water go past, and it could drip out, right? My thumb wouldn't have much of an effect on it. But what would have to happen for my thumb to have a big effect on that?
Volume.
Crack that thing right open. Volume, exactly, volume, that's the key word. So in engines and air pump, if I try to flow more volume through it, that will flush restrictions to the surface, won't it? So this was a double thing. I tried to do 2 tests at the same time. One, As soon as I started the car, I was looking for a timing error. If my exhaust cam shifted and my valves closed early, remember that last case study at 360 we had that hump? I was looking for that. The moment I didn't see that, no problem, I just went like this and opened the throttle. What did the engine do when I opened the throttle? Took a huge gulp of air, and that air couldn't go anywhere because the exhaust, it couldn't be blown out the exhaust. So as a result, back pressure started to increase. If you guys zoom in if I zoom in real close here, you guys got to look carefully. Here's a compression tower. Remember, I got seconds on the screen here. I got a lot of time on the screen here, like 2 or 3 seconds. Think of how many combustion events occur in 2 or 3 seconds. Here's a compression tower. Here's a compression tower. Here's a compression tower. If you look closely, here's where EVO happened, and here's the exhaust plateau. Okay? Right there. So if you watch it, I hit the gas. You could see compression go up because I opened the throttle. Look at the pressure here. It's starting to climb and climb and climb and climb. Back pressure. Upwards of 30 psi. Can that engine breathe if 30 psi is inside the exhaust stream? It can't. If it can't exhale, can it inhale? If it can't inhale, can it pull down on the intake manifold? If it doesn't pull down on the intake, will the map voltage go up? If the map voltage goes up, will the PCMC load and give too much fuel? If it does that, we don't need the fuel. Will the O2 sensors report rich and then we pull negative fuel trim? That's exactly what happens here. So under snap throttle, volume increased, so did back pressure over 30 psi. The spent gases have nowhere to go, and the cylinders can't breathe. The back pressure prevents cylinder fill, and the intake pressure rises as a result. Look, new cat. Look at that. There's the back pressure. I snapped the throttle. You see the engine rev up. See that line there? Stayed the same. Why? Because there's no back pressure. There's no restriction. 0 psi back pressure. The cat was restricted. The customer confirmed a misfire had been corrected recently. Listen to the significance of that statement. The cat melted down. Cats don't melt down by themselves, do they? A cat, it doesn't just melt down, does it? Yeah, they go bad and they get sintered and they don't do their job anymore and they don't convert these nasty gases to something more breathable. But they don't melt down by themselves and get restricted by themselves, do they? Something had to kill this cat, didn't it? So if I put a cat on this car and didn't go any further, is there a potential this would come back and somebody's very unhappy? There is. Yeah. So what I did was I interrogated my customer. Before I went any further and I knew I had a cat, I said, hey, Mr. or Mrs. Customer, how's this car running? Oh, it was fine up until last week. You know, Larry took it to the grocery store and it started running funny, so we brought it to my guy and he fixed it. It was shaking, but now it's not shaking anymore. What did she have? She had a misfire, and it's running good now. Well, right, a cat damaging misfire, but she doesn't anymore. So I confirmed the root cause of the problem was repaired already. Now I'm just fixing, the result of that root cause, the effect of it. So by putting a cat on and already confirming the misfire's gone, I can take it for a road test and feel confident the car's fixed, right? That's what I did. But more importantly, let's talk about the chain of events. The cat was replaced. We did another in-cylinder snap. It looks good. Confirmed the fault's eliminated. The cylinders can breathe again. The map signal returned to a value reflecting strong manifold vacuum and low load. As a result, the PCM fueled accordingly, and there was no need for fuel trim. Fuel trim stayed within 3% correction. Is the car fixed? It's fixed. So the misfire overheated the cat, melted it down. The restriction prevented the cylinders from exhaling, so they couldn't inhale. Manifold vacuum suffered as a result, and in the eyes of the PCM, that reflects load and the need for fuel. Through the eyes of the O2 sensor, unnecessary fuel is reported to the PCM, and negative fuel trim results. Within cylinder testing, timing was eliminated, and the restriction was proven in one test without any disassembly whatsoever, other than removing a spark plug. How powerful is that? No broken exhaust bolts, no exhaust O2 sensor threads being damaged. I've broken oxygen sensors trying to take them out. Some of these things are hundreds of dollars. Hundreds of dollars. Okay, let's move on to the next one. And again, if there's any questions,
One quick
yeah,
one.
please.
If we had changed this from a 4-cylinder to a V6, and we had our trim information would have been different from one bank to the other.
Very true.
And then that would have given us an indication, I mean, to see that it's gonna matter if they got two individual cats.
You're right.
which bank you test with that.
Exactly. What's going to happen in this case, if this was a speed density system, okay, you'll,
V6 Honda.
yeah,
With
right, with a V6 Honda that has two separate catalysts, okay? If the point of restriction is common, it's going to affect both banks. If
Right.
one cat is restricted on one bank, this is a speed density system, so you're going to have elevated map voltage and a similar symptom. However, the engine bank that is suffering from breathing is going to have more negative fuel trim than the other bank. They're both going to be screwed up because of the elevated map.
Right.
But the side with the restriction is going to have even more negative.
That's the side
Okay.
you put your sensor.
Yep. A mass airflow system is going to respond similarly, but they're going to be directly opposite of one another. One's going to go up and one's going to go down. And I cover that in some case studies later, and we'll be back next time to cover that more in depth, but that's a great question. Now this next one here is a cylinder. This does have a loss of volume, but it's due to a very late intake cam. So check this out. Low peak compression. We beat the heck out of this characteristic. When an intake cam's late, all the volume gets pushed back into the intake until that intake valve shuts. Now if you look closely here, I might be able to zoom in close enough so you can see this. You see, that's where the intake valve closes on this. Now I got to zoom out again. Right there. It's supposed to close at about 60 degrees after bottom dead center. It's closing all the way over here like 90 degrees. Like we got another 10 degrees, or excuse me, 150 degrees. We got like 10 degrees of crankshaft rotation to go to capitalize on the rest of that stroke. So there's like this much air in that cylinder. But remember, single camshaft. One cylinder's going up, one's going down. As this one starts to come down, the next cylinder comes up on compression. And it too has the same thing, very little contents in it. So what's going to happen to crankshaft speed? If I'm going up on compression, I got nothing to squeeze. It's going to speed up. So the whole crankshaft's going to speed up, which is going to drag this one down real fast. That's what happened there. The crankshaft went real fast here. That's what pulled it down and caused that to lean. We know the pocket differential for the same reason here. Remember our syringe? We let all the air out, and when we get to the top, then we put our thumb on and we're drawing against closed valves. The vacuum's relieved as soon as the exhaust valve opens. That's what causes that huge pocket differential there. And of course, there's defined valve events. We see EVO, we see IVO. IVO is actually right here. The piston starts to pull down and down and down until the intake valve opens. It's supposed to open over here, but it's opening very late. That's what's causing this pocket here. This is a cranking waveform here. It almost looks like a running waveform with bad compression. So here's a cylinder loss with the late intake cam. This is another one here. Okay, low compression indicates the inability to harness and squeeze the contents. The leaning towers indicate the cylinder lost pressure at a faster rate than it produced it, suggesting a loss of volume. Again, that's because the next cylinder going up on compression. The pocket differential confirmed a volume loss. Again, our syringe analogy. And defined valve events indicate a rapid change in pressure at EVO, IVO, and IVC, indicating valve sealing is not compromised. So that's the difference between condemning an engine and jump timing. If you heard this engine cranking, you'd have swore this engine was done. Chains slapping around and everything, it was a nightmare. You should have heard this thing, but looking at this data, it didn't need an engine, did it? Just timing chains. Timing components, excuse me. So that's a result of a very late intake cam. Now this is from my good buddy, Bryn Klein in Florida. Me and him and a group of guys all over the U.S. and now other continents too, talk to one another on a regular basis. And we corroborate on a lot of different cars. And we just have fun doing it, helping each other, and we constantly learn from each other. So this car here, Bryn got from, Bryn has a reputation at his, him and his shop in Melbourne, Florida called Assured Auto Works. They have a reputation for being almost like a last chance shop. I mean, they get cars from other shops that are dumbfounded. They don't know what to do. And Bryn solves a lot of their problem. Him and his guys are really good. So they got this car in there. Now the other shop had it, and it had a bunch of cam codes from what I remember. And it turns out after disassembly, it had a cylinder head. First of all, it was like an auction car, so they didn't have any history on it. But it had a cylinder head from like a junkyard, or it had an indication that at some point it went to a machine shop. It had one of them hot buttons on it. You know the ones that fall off when they get too hot? And it had a broken camshaft reluctor. Now the camshaft on this engine, I think this was a Chevy Aveo, twin cam 4-cylinder. One of the, if you guys can picture that, one of those camshafts in your mind, the reluctor was broken on it, physically broken, so they had to put a whole camshaft in it. So when the other shop got it back together, the car started and ran, and there was no codes, but it ran like crap. It had no acceleration. It didn't sound like it was breathing right. So that's when they brought it to Bryn. So Bryn looked at it, and the first thing he did was scope the camshaft position sensors, both of them, and the crankshaft position sensors, and they all lined up perfectly. So, you know what I mean? Bryn grabs the low-hanging fruit too. He knows what to do to get himself headed down the right direction. So everything's pointing to nothing wrong with cam-crank correlation per se, but let's go see if the engine's breathing right. Let's go for a road test and look at VE, volumetric efficiency. So his plan was to plot traces for throttle angle and for RPM and mass airflow, and he was going to do some math and figure out if the engine wasn't breathing right or if it was underfueled or something. Well, this thing, what happens now on newer vehicles when we go like this with a gas pedal? Is that a command? It's not a command, it's a request now, isn't it? We asked the PCM to open the throttle. He was asking for this. It was only giving him this. Can an engine breathe properly with a closed throttle? So is a volumetric efficiency test going to be of any use to him here? Not at all. So now he's limited on what he can grab as far as low-hanging fruit. Are you with me so far? So he went in cylinder with a compression gauge, a pressure transducer, and he gathered some data. And he compared what he had in cylinder. It looked very strange, just what he had here. And you and I recognize this as a late intake cam, right? We can see this is late here. You know the significance? The cylinder pulling down on the syringe before the intake valve opens? We're starting to see that here. So he immediately sees that and thinks something's screwed up. But again, it doesn't corroborate his cam timing signals. So he starts going on to databases and looking for known good captures. And again, we reached out to people all over the United States. And a lot of people, like 7 or 8 people, got involved in this car. And it turns out this is a picture-perfect waveform for a 2011. Don't quote me on the years. I'm just giving an example. For like a 2011 Chevy Aveo. But a 2009 looks nothing like this. So it got Bryn doing some research. Nothing was adding up. He got to the point where he had to rip this engine down and physically inspect it, and everything looked good. There was nothing wrong with the cams. There was nothing wrong with the lobes. So we were missing something. It turns out there was a handful of different camshafts available for the same engine depending on what application it was being used in. And as long as the PCM knows that, we're okay. This has variable cam time, and we can compensate for that. But if the PCM thinks it has this cam in it, but it really has this cam in it, all hell breaks loose. So that's what happened. So in the end, it's a late intake cam. It's almost as if the cam lobes spun on the shaft is what happened. The timing signals stayed perfect, but the cam lobes aren't in the same spot. So this is it side by side. So here's what a good one should look like for this engine. Peak compression at 203 psi. Intake valve open at about 5 degrees before. I know this is very hard to see. Again, this is a cranking waveform, so we don't produce much vacuum there, do we? 1 or 2 inches of mercury. That's why you can't see this drop down too far. But it drops down about 5 degrees before bottom dead center. Okay? Oh boy. Bear with me a second.
Need batteries?
No, this thing's there we go. I was still stuck in a mode here. The intake valve closing is at about 50 degrees after bottom dead center here. Okay? This is result of a cam that is in proper time. Now look at the one that he had in his car. Peak compression was only 141. The intake valve wasn't opening at 5 degrees before bottom dead center. It was opening right here at 35 degrees after bottom dead center, about 40 degrees late. Intake valve closing at about 74, not 50. So we're way late here. Okay? He ripped this car apart. Now I asked him to take a picture of these cams, and I uploaded these pictures to a paint program to draw some dots on here. In hindsight, I should have kept the red dots pointed at 12 o'clock and showed you where the lobes fell. And if I did that, you'd see this lobe would be way over here. Now we're staring at the back of the camshaft, the driver's side. The cams, he's on the front of the engine's on the passenger side. They'd rotate this way. So this camshaft would be over here. This lobe would be very, very late. Do you guys see that?
Yeah.
So it's extremely late. So this would be the equivalent as if you had one of those camshafts where the lobes were pressed on, if they lost their point of reference and spun on the camshaft. Think of how difficult that would be to find. Breathability, you can see a camshaft once those lobes spin. This thing was machined this way. The timing marks are perfect. There's no DTCs. You can't drive the car. It breathes like crap. Your in-cylinder waveform says there's something wrong. You rip it apart and the cam is in perfect condition. What are the odds that there's multiple camshafts available for this same engine? I'm just telling you, these are some of the stuff you're going to be faced with. And without this information, I don't know how he would have proven it. It would have been a long battle, right?
They are.
What would you replace
That's
if
a
the
big
cam was in time and you took
If
the
it
cam
came
out, was
from
in
the front.
perfect condition? Wouldn't you feel like there's just something, you don't know what you're doing?
Brutal.
Be a little bit.
Shit
There's
people
nothing
throw
wrong
in.
with the cam physically, it's perfect. So this was a
Anything
tough one to
happens there.
find.
And every
Okay, part of learning, I like to fix cars forward and learn backwards. Now stick with me on this one. We talked about working on known good cars. I also like testing like this on known good cars. I also like testing on cars where I know what's wrong with it. I'm in control of the experiment, right? The conditions here. So this car was towed in with a broken timing belt. This car, I think it was a Dodge twin cam. I remember that. But it doesn't matter what engine's it in, just that it's a 4-cylinder engine, okay, with twin cams. It's towed in as a crank no start. Of course, we know what that sounds like, no compression. The timing covers were removed just to confirm a broken timing belt before we called the customer. The best way to learn, again, is on known good vehicles, but unless you know the conditions you're testing on, as long as you know that, you can
good.
take
You
good
have one to
notes.
compare
You can test, I call it testing responsibly.
But who drives
So
them?
the first thing I did was I try to gather as much data as I can from all different points, all different perspectives, and see how they correlate. And I never looked at a car with a broken timing belt before. I just wanted to see what it looked like. So what I did was with a relative compression trace using an amp probe and a lab scope, I won't get into the details yet, but using the lab scope and amp probe, I could see a tall peak every other 360-degree turn. Okay, so I don't know what's going on there yet. I didn't think about it. But relative compression test displays a tall peak every 360. Volume comes to mind there. Engine configuration also comes to mind. Let's save this for later, move on to in-cylinder analysis. So I put my pressure transducer in cylinder number 1 and I crank the engine over. First, the in-cylinder waveform displays low compression. That's at about 71 psi cranking. Cranking, it should be like twice that, okay, 140. But we're only at 70. I also noticed straight towers and even pockets. So is this cylinder leaking down? It's not leaking down, but we see the nice round pockets indicating what didn't happen. The intake valve didn't open and the exhaust valve didn't open. Of course they're not. The cams aren't turning, right? Just food for thought. So let's talk about this. Picture a twin cam engine, a 4-cylinder design, and picture the pistons, companion cylinders working together. Okay? Companion cylinders, 2 adjacent, 2 ascending, 2 descending. Cams are stationary. More volume is harnessed in one crank rotation compared to the other crank rotation. Check this out. We're going to talk about how to use a piston chart later, but basically the piston chart's configured for the firing order of the engine. And basically wherever I reference, like an ignition sync on cylinder number 1, that's how it starts the firing order. So if I change that sync to 4, it would start the firing order 4, excuse me, 2, 1, 3. But since we started with 1, it's going to start the firing order at 1. And basically this piston chart allows us to associate all the cylinders at any point in the 720-degree engine cycle. So what we see here for cylinder number 1, the one we were just in, at top dead center compression, the valves are closed, right? Obviously. We trapped air in there and we produce compression. So then we got to go to the next cylinder in the firing order, cylinder number 3. Bottom of the intake stroke. Valves are open, right? The intake valve's open. We're trying to draw air in, okay? We don't close the intake valve till 60 degrees afterwards. So the first cylinder, cylinder 1 sealed, intake valve's open so it's in red because it can't seal. Cylinder 4, next one, top dead center of the exhaust stroke. The exhaust valve is open. Maybe the intake valve as well. That cylinder's not sealing, is it? Then we go to cylinder number 2 here. We're at bottom dead center of the power stroke. The exhaust valve opened 45 degrees before that. That cylinder's not sealing either, right? So we know one cylinder is sealing. That's when we go back to our relative compression trace, right? Every time that engine goes around, every 360 degrees, we get a peak in compression, and that's why it affects our relative compression trace. Does that make sense? So I'm trying to put the puzzle pieces together. This isn't very important, but my thought process on how to gather data is. That's what I'm trying to reflect to you guys. You have to try and associate different tests, see how they line up, see how they overlap. So relative compression test presented as such due to companion cylinders. 2 consecutive compression events. One compression event harnessed more volume than the other. Rounded pockets confirmed no exhaust valve opening or intake valve opening. In-cylinder analysis reflected low compression because the cylinders couldn't fill. There was very little volume to compress, if any at all. Straight towers and even pockets confirmed no leakage. Okay, let's move on. If I lost anybody on that one, write into G and I'll answer any questions I can. So this is a capture from a 2.4 liter Honda, about 2002, 2003, the K-Series engines. It doesn't matter, but what I'm trying to show you here is this one has variable cam timing on the intake cam only. And we talked about normal numbers, intake valve typically opening at about top dead center. This one's opening way late. So what does that do to overlap if we open the intake cam late? Gets rid of overlap, doesn't it? So think of what that does to idle stability. If we don't inhale exhaust gas, we get more stable combustion event. This is a 4-cylinder engine. These combustion events are spread out every 180 degrees, so just by design, this engine's going to run rough compared to something with more combustion events in any given engine cycle. But now we can lower the idle down to like 400 or 500 RPMs and still have this thing run smooth. We have cam timing advancement on the intake side to help with cylinder scavenging under acceleration and to help have the best power and in different RPM and load ranges. So it gets optimal performance at all different RPM and load ranges. But what I want to show you here in this capture is pay attention to compression, pay attention to the exhaust ramp, pay attention to the point the intake valve opens, the intake valve closes too. I'm going to show you what happens when we phase this camshaft positively. First of all, I want to point out the intake valve's openings occurring at about 30 degrees after top dead center here. Note the position of the exhaust valve opening, the ramp, where it falls relative to this 180 mark. It kind of goes right down the center of it. Note the amplitude of the compression towers here. And the intake cam is at base timing. This is what it looks like when there's no phasing taking place. But in this next capture, what I did was this high side driven oil control valve circuit. It's always grounded and it gets a positive pulse width duty cycle from the PCM to energize it and allow camshaft phasing. I jumpered voltage to it with a jumper wire and made it wide open so it would phase the cam positively 30 degrees. Look how high compression went. The exhaust valve didn't move at all. Why not? It's on the intake phase. But this shifted to the left, didn't it? It used to be out here. Now it's all the way here, which caused the intake valve to open early and the intake valve to close early. That's what made compression go so high. So intake valve's occurring at about top dead center now. The exhaust ramp didn't move because it only has intake variable timing control. And the amplitude of the compression has risen because the intake cam's advanced. Here's a side-by-side, before and after. Look at compression. It jumped way up. Again, exhaust cam ramp didn't move because we don't move the exhaust camshaft. The intake cam did move, which caused the intake valve to open early but also close early, right here. Here's at about 75 degrees. Here's closer to 45 degrees before or after, and then our compression went up here. So advancing the intake cam, again, opens the intake valve sooner, but for valve overlap and cylinder scavenging to increase breathability. Advancing the intake cam closes the intake valve sooner, traps more air in the cylinder, and increases compression. In-cylinder testing allows for a dynamic view of the system of the components functioning together. We could see it live. So everything starts in inside the combustion chamber. Let's move forward to the intake manifold waveforms to show you what happens, what's occurring in the cylinder, and how it affects the intake manifold. So here I got a picture of 3 lovely young ladies enjoying a non-alcoholic beverage. But really what I'm trying to show you is they're reducing pressure inside the straws, which gives atmospheric pressure more capability of forcing the fluid up the straws into their mouths. This is how an engine works. We inhale air this way by displacing it. The intake manifold is nothing more than a storage tank. Each cylinder pulls on the intake in turn. Cranking vacuum waveform will present differently than idle vacuum waveforms for the same reason why cranking manifold vacuum with a gauge is 1 or 2 inches of mercury at idle, cranking where we might get 20 inches of mercury at idle. Okay? We're looking for anomalies that differ from cylinder to cylinder now. Again, we're not looking in cylinder, we're looking at the intake manifold and how every cylinder in that engine is affecting it. This can be correlated to events within the suspect cylinder. I'm going to show you how to do that here shortly. This is just a piece of the puzzle. I don't look at these waveforms and make a decision about the engine and hang my hat on it. I use this to give me more fuel to drive down to a more pinpointed test. Okay? So anybody in here on IATN? If you are, you will certainly recognize the name Albin Moore. Albin is a sweetheart of an old man. He's been in the industry for a very long time. He has a lot of wisdom. I spent a week with him and his lovely wife Alice in the state of Washington, and he was kind enough to let me stay with him to learn from him because he had a good handle on pressure waveform analysis, and I wanted to learn from him. Excuse me. So I called Albin and I asked him permission if I could use some of his waveforms in my presentation because Albin has a knack for doing experiments and documenting his results of experiments, but better than that, he shares them with everybody and explains the results. So I want to show you what I know about these waveforms. Now keep in mind, these are screenshots, so I have no ability to actually manipulate the waveforms. What I'm getting at is I would love to turn this blue channel off to get it out of the way because we don't need to see it, but I can't.
What is the blue channel?
The blue channel is ignition events, and I don't remember the car he was working on.
Oh, he's on a, so that's all of them. No.
Yeah. Okay, so I don't know what he's working on, but it doesn't matter. We're going to ignore the blue trace, and we're only going to look at the red trace, which is in-cylinder compression while this engine's cranking. And the green trace is from an FLS sensor attached to the intake manifold. So to recap, what happens to an FLS sensor when you introduce vacuum to it? What happens to the trace? Which way does it go, up or down? It goes down. Okay, what happens to it when pressure is introduced to it? It goes up. Okay, so in red we have an in-cylinder compression waveform, cranking. Okay, in green we have the FLS trace. The FLS trace is showing us the effect of all the cylinders in this engine pulling on the intake manifold. So how many pulls are between the two compression towers? 1, 2, 3, 4. How many cylinders are in this engine? 4. You guys see that? What we're looking for is differences between the intake poles. I have the intake poles highlighted in yellow there. Again, the green trace is the FLS sensor connected to the intake manifold while the engine's cranking. Vacuum makes the trace head south. The pulls occur when the piston is descending on the intake stroke when the engine's cranking. A pull will occur with sudden exposure to the intake manifold when the engine's running. Okay? So the yellow arrows indicate when a piston pulls down on the intake manifold. The orange arrow is showing us when this cylinder induction stroke occurs, it creates this pull. You guys see that? Piston goes up, piston comes down, exhaust valve opens. Piston's heading up here till we get to top dead center. The piston changes direction and starts pulling down, and that's what's drawn here. What I want to point out here is this. Top dead center, top dead center. We know that to be 720 degrees, don't we? If I drew a line right down the middle here, that would be 360, wouldn't it? The first pull to the right of the 360 mark is the pull created by this cylinder. Does that make sense?
Yeah.
So, if the firing order was 1, 3, 4, 2, and this is cylinder number 1, and had an ignition event here, it would be 1, 3, 4, 2. But in regards to the poles, this would be 1. So 1, 3, 4, 2. Does that make sense?
Yeah.
There's a shift in phase of 360 degrees from a compression event to an intake event for the same cylinder. You have to understand that. Here's that same capture. I tried to clean it up in a paint program as best I could so I can annotate it. And that's what I'm getting at. Here's 720. You can see this is 360 right here. Let me see if I can zoom in on that. This is 720 from here to here. Right in the middle is 360. The first pull after 360 is for this cylinder. 1, 3, 4, 2. If that does not make sense to anybody, let G know, and I will see if I can clear that up a little bit. Come on now. There we go.
Just one thing,
Please.
Question or comment. This goes on any engine? A question, actually.
Any engine. I'm sure there's something that I didn't think of, like a rotary engine. I never gave that some thought. But yes, we're talking about dual overhead cam engine, single overhead cam engine, 4-cylinder, 6-cylinder, 10-cylinder. If you have 720 degrees to complete an engine cycle, you have 720 degrees. No matter what you change there, you can't change the fact that every 360 degrees, a crankshaft rotates one time around. That's when our intake stroke has to start at 360. So no matter what engine design you have, yes, that same rule is going to apply. The first pull after 360 is the pull for the cylinder that we're measuring here. I hope that cleared things up for you.
Yeah, says thank you.
You got it. So the pushes are created by overlap and displacement. Remember, an intake valve opens, right? The exhaust valve is already open. So for a moment, we lose vacuum in the manifold. Very little bit, but we do, don't we? That causes this to go up. Same here. The piston starts to head up on compression here till we shut the valve. That's what causes this to come down. So that's what causes the pushes versus the pulls. Okay? I'm going to display that better in some captures coming up. Some better examples of what's actually going on here. So again, the pull for the subject cylinder is always 360 degrees away from the compression event. So now let's do some experiments here. I love Albin for this. This really knocks it out of the park. So you see on top here, this is the actual scenario. This is going to be a cranking intake waveform versus in cylinder. We tightened an intake valve to the point that it left its seat a little bit. Understanding we are losing some volume past the intake valve, back into the intake manifold with loss of compression. So I want to ask you this. The red trace is in-cylinder compression. On the same cylinder we screwed up the valves on. If I tighten the intake valve, what would happen to some of the charge in the cylinder when the piston approached top dead center of the compression stroke? Where would it leak to? It would go to the intake manifold, right? So if I'm pushing volume into the intake manifold, what would happen to pressure? Even if it's a little bit, but what would happen to pressure in the intake manifold? It's going to increase. If I have my FLS sensor on that intake manifold at the time, what's going to happen to the green FLS trace? It's going to go up. Is that not what we see here? If I took away that red trace and we were only looking at the green one, would we not see a tall pulse every 4 events? We would. Let's see how it correlates to in-cylinder. So we tighten the intake valve, our piston goes up on compression, some volume goes into the intake manifold and pressurizes it. Check this out. This is cool. You see that blue circle there and there? Remember, this is pressure over time. What that means here is pressure stayed the same for a little bit of time, didn't it? And then pressure decreased again. I want you to picture a crankshaft journal through the cycle. If we start here and our piston connecting rod's connected to the crankshaft's going to overcome top dead center and slowly the piston's going to descend until we get to about 90 degrees. Then it's going to fly down, isn't it? And then when we get past 90, it's going to slow down again until we get to bottom dead center. This is so sensitive. We are seeing the change in piston speed in the intake manifold. Why? Because the intake valve's open and we're on the intake manifold. We're seeing the results of what's happening with this cylinder through the intake manifold. Can you see that? I know I probably lost some people on that, so gee, keep an eye out. But this is showing a change in crankshaft speed. Pressure over time, this trace tells us the pressure stayed the same, no change, for a little bit of time. That means the piston slowed down and then speed up again. It's pretty slick. Some other aspects of this waveform I want you to pay attention to. I'm trying to show you how to associate what's going on in the cylinder with what's going on in the intake manifold and how it's reflected by the tools we're using. So the tall push is at top dead center compression. The blue circles indicate the FLS reflecting change in pressure. That's because the piston speeds up at about the 90 degree mark after top dead center and then slows down again. Slows down and then speeds up again. The weak pull as the piston ascends because of displaced volume. Let's look over here. A pull, a pull, a pull, a pull. This pull is weaker right before we go up on compression. This pull is weaker right before we go up on compression. If I tighten a valve, we increase duration, don't we? We open up the valve sooner and we close it later. If I close the valve later, our syringe, right? We push a little bit of volume back into the intake manifold, don't we? Oops. If I push volume back in the intake manifold, isn't there another cylinder going down on induction? One's going up, one's coming down. If that cylinder's pulling on the intake manifold, picture the girls with the straws. If one girl's drinking out of the straw and the other girl's spitting fluid back into the cup at the same time, is she really going to get anywhere? That's what's happening right here. I'm serious. I'm trying to make an analogy we can wrap our heads around. This piston's trying to dump volume back into the intake manifold. And so if this is cylinder number 1, this is pull number 1, pull number 3. And cylinder number 3 is trying to inhale, and cylinder number 1 is spitting it all right back into the intake. They're fighting each other. That's why this pull for number 3 cannot be as deep. Does everybody see that? Yeah. Does it make sense? Let's move on to another. Oh, and pocket differential. Let's not forget about that. Let me go back to the good one with no leakage. Look at that pocket differential there. Very little, right? You're going to have a little bit of seepage past the rings when you're cranking an engine over. Every engine has that. You have to. Otherwise, you're going to damage the cylinder walls. The rings will be too tight. There's always going to be a little bit of blow by cranking. So you're going to have some pocket differential. It's normal to see that when you're cranking. The key is how much. We have very little here, right? Because of little leakage. Look at this one. Since we cranked the valve open, look how much pocket differential. You guys see that? That's what we don't want to see. Okay, let's move on to the next one. Again, if I lose anybody on anything, please feel free to respond, and G will ask me some questions. I'll see if I can clear anything up for you. Here's a tight intake valve. Same scenario, except this time we only got rid of the valve clearance. We did not tighten it so the valve left its seat. Are you with me? There is no loss of compression here. So there's minimal pocket differential here. Again, we didn't lose any volume. No change in cranking cadence. We don't hear anything because there's no loss of compression. There's a weak pull due to displacement from late IVC. Same thing. Cylinder number 3, the girl number 3 is trying to suck some fluid out of the cup. Girl number 1 is trying to spit the fluid right back in the cup. They're fighting each other. That's why there's a weak pull there. And again, a weak push at top dead center compression. You see this here, how this one's lower? Remember that paddle ball? The sling, the bounce back effect? If I grab this green trace, watch me here, and I grabbed this and I pulled it down like this, and it was elastic, wouldn't it fly way up high? It would, right? If this was like that paddle ball, if I pulled this thing way down like this and let go, wouldn't it fly back? What if I only pulled it a little bit? Wouldn't it only fly back a little bit? You see that? That's that characteristic right there, that flyback characteristic. If we weren't aware of it, we could screw our results up, our interpretation of the results, I should say. This one's really going to make sense for you. This is a loose intake valve. Think of duration. Think of when a valve opens when it's loose. It's going to open late, so check this out. There's a steep descent of the FLS trace due to a rapid change in pressure. Let's go back to the syringe for a minute. If I open up an intake valve late, normally we go like this, and then we pull the piston down, right? To inhale an air charge. If my intake valve's late, I'm not going to go like this. I'm going to start pulling the piston down first, right? It's going to evacuate that cylinder and draw it into a vacuum. Where does that vacuum go when the intake valve finally does open? To the intake. So what you're saying is no matter how much, it is going to pull some vacuum on the intake a bit more than before, right?
Pretty fast, too.
Yeah, puh, right? It's going to suck down real hard. Look at this green trace. If your FLS sensor was attached to the intake manifold, if it was attached to it, wouldn't it reflect that same deep vacuum pull, that really rapid change in negative pressure? Negative change in pressure? Right? It should, shouldn't it? Did I lose you guys? Everybody got quiet all of a sudden.
Is that what creates reversion?
What do you mean by that? Can you explain that?
I know kind of, I got burned by it a long time ago by something dropped the valve seat and pulled the intake off to the side, did the head, lit it up, and of course something peened the plug closed because
Contact, yeah, you hit
stuff
something.
ended up, but it got sucked back into the intake. I was told by reversion is what.
I'm not sure how to answer that.
Okay.
Okay, I'm sorry.
Yeah.
We'll have a private conversation
Okay.
afterwards. I don't know.
Okay.
But basically, what I'm getting at here is the cylinder, it's like pulling the syringe down with your thumb over the end and pulling a vacuum in the cylinder. You can see that occurring here. We're pulling a slight vacuum. But when the intake valve finally does open, that vacuum goes away. Where did it go? It went to the intake manifold. And we could tell that right here because this FLS trace drops straight down. Indicating what? A rapid change in pressure. Which way? South. Right? Pressure dropped rapidly. That's what that says. So the tall pressure spike in cylinder is due to the early exhaust valve closing. This is a different one here. Cranking intake waveform, this has a loose exhaust valve. We recognize this trace from a while away down, don't we? Intake valve, exhaust valve closing early, right? The exhaust valve closes early because of a loose exhaust valve. We're going to trap exhaust gases in the cylinder as the piston approaches top dead center. Because the area is getting smaller, pressure has to go up. Pressure goes up until what happens here? What causes that to drop suddenly? What valve opened? Okay, if the intake valve opened and there was pressure built up in the cylinder, where did the pressure go? Into the intake. If my FLS was connected to the intake, would the FLS trace go higher or lower? Higher. Isn't that what we see? We built pressure up here till what? The intake valve opened, pressure in the cylinder dropped. Pressure in the intake manifold rose, and that's what caused that positive spike in the FLS trace. Does that make sense? Yep. It went way high, but look what happened. It sprung back and went way low too, right? That's that bounce back effect. If you weren't aware of that, you might try to make a decision based upon this. That would be a mistake. It's just that flyback characteristic, that bounce back characteristic, just like those paddle balls. That's why I use that analogy. It's easy to remember that, isn't it, when you think of it like that? So the tall push in the intake waveform was due to the rapid pressure change when the intake valve occurred. the volume that was trapped in the cylinder was delivered to the intake during the intake valve opening event. Okay, here's the next one. This is a tight exhaust valve. But again, no volume is being lost. We just took up the clearance on the exhaust rocker. Normal cranking cadence. Again, why? We didn't lose any cylinder charge. Rounded exhaust pocket. Remember the characteristics of a tight valve? We want rapid changes in pressure. When you have a valve that's tight, when you have a valve that's of proper clearance, of a decent amount of valve clearance here, your valve's going to follow the profile of the cam lobe, your rocker, but not until all that clearance is taken up is that cam lobe going to have an effect on the valve movement. If you take away that slack, the opening of the valve is going to follow the profile of the cam lobe. It's going to be really soft and transitional, right? Rather than a rapid change, you're going to have that rounded effect there. Really tough to see, but see how round that is? We wanted that sharp change. We don't have that here. That's due to a tight valve. Let me go back here. Bear with me a second, okay? So the rounded exhaust pocket. We have no excessive pocket differential for the same reason we don't have any leaning towers and we have normal cranking cadence. There was no loss in cylinder charge. The weak pull, though, we have in the intake manifold is due to excessive overlap. If we tighten a valve, we increase duration, don't we? We open it early, we close it later. If we close it later, when the induction stroke does happen right here, not only are we pulling on the intake manifold, but we're sharing some of that pull with the exhaust. Meaning, our intake pull is not going to be as strong on the intake manifold. And isn't that what we're seeing here? If that's 720 from here to here and that's 360, the first pull after 360 is the one for this cylinder. If that cylinder has a tight exhaust valve and more overlap, we're going to have a weak intake pull. Is everybody with me here?
Yeah.
The pull, again, is shared between the intake and the exhaust due to that overlap scenario. What I mean by overlap is this shaded area you see here, it's going to spread when you tighten any one of those valves. When you tighten this valve or you tighten that valve, those ramps, they get wider. And if they get wider, they overlap more. That gray area will get bigger. And that piston is going to pull down on the intake manifold, but it's also going to pull on the exhaust, and that's why we get a weak pull. Again, if I lost anybody, please write in, and I'll try and clear that up.
I have a question just
Yes.
about the green trace you have with the delta sensor. Rather than have to read between the lines on how a delta sensor performs, do you ever use an absolute?
Absolutely I do. Yep.
And what benefits? And so, I mean,
Absolutely I do. Yep. Unfortunately, some of those case studies you're talking about, Leo,
yeah.
I use a lot. We're going to cover
do both.
when I do both.
Yeah,
Yep.
okay. All right.
And I actually prefer the absolute because I don't have to worry about these characteristics
Right.
that I got to overcome and see past, right? Just like look.
But you know how to read it, and it's an easy sensor to use.
That's right.
Sometimes
It's
you don't
very
use it.
inexpensive,
Okay.
right? And you don't need any special device you can plug it into any scope. It creates an electrical impulse.
All right.
If you could look at voltage, you can look at that. But you're right. I prefer absolute because there's none of that crazy stuff. There's none of that flyback. You know what I mean? And we're going to demonstrate that in part 2. So valve overlap is a duration of time when both the intake and exhaust valves are open simultaneously. It's essentially linking the intake and the tailpipe to the cylinder. All three are going to be exposed to each other at the same time. Overlap reflects in the pushes and the pulls because of pressure changes, and excessive valve clearance decreases duration, where tight valve clearance increases duration. So any of you guys that are on IATN, tremendous source of information. Now we got Diagnostic Network, which is like IATN on steroids. So if you're not on Diagnostic Network, please find it on Facebook, find it on the internet, and make sure you sign up. Tremendous, tremendous asset to our industry. But anyhow, back to IATN. So years ago, I was learning how to use this stuff, and I started to do an experiment. I had another one that came from another technician that the valves were misadjusted. They weren't tightened properly. He goofed them up. The car wasn't running funny. It was running funny. So I made arrangement with Mr. and Mrs. Customer to leave the car with me overnight for a couple reasons. I wanted time to mess with it, but more importantly, I wanted the engine ice cold to eliminate a variable from my experiment. And I wanted to hang a battery charger on it, a constant voltage battery charger, to keep this engine cranking over at the same speed no matter what I was doing, whether it was before or after. It didn't change. Because remember, cranking speed affects cylinder fill and will drastically affect pressure, okay? So what I was going to do was this. I was going to put my FLS sensor on the intake manifold, and I was going to crank the engine over for multiple engine cycles and save the data. I was then going to go into the engine, pull the valve covers, and measure all the valve clearances. And then after I measured the valve clearances, I was going to adjust them to specification. I was then going to reassemble the engine and repeat the test and see the results of my findings. I had a hypothesis that I could detect valve overlap using an FLS sensor while cranking as a preliminary check. Something I can do in 5 seconds. So here's what I did. Again, this is a 3.5 liter Honda. It had a rough idle. Symptoms vanished off idle. PO300 stored to PCM. The fault was present before service was performed. Was not present, excuse me. So it happened after the guy adjusted the valves. The experiment we just discussed, I wanted to see if I can detect overlap through the eyes of the lab scope and the FLS sensor on the intake manifold. So here it is. Here I got an old 20-year-old Snap-on Modus. You can use this stuff with even something this old and be accurate. I learned on this thing. So what I have here is all 4 traces on. 1, 2, 3, and 4. Yellow, green, blue, and red. And what I did here was this. Red and blue, again, are turned on. The traces are active, but they are just flopping around in a breeze. They're not connected to anything. I use that as a visual point of reference to create a ceiling and a floor. So you can associate this green trace, you know, the difference in amplitude here. It makes it easier on the eyes. My yellow trace is connected to number 4 coil command. I used it as a point of reference to not only infer when an engine cycle completes, but also to tell me which cylinder each pole is associated with. If I know the firing order and I know what cylinder this is attached to, I can figure out which pole is which. Why did I choose number 4? Right, I'm a lazy son of a gun, and it's right next to the radiator, and I don't want to be leaning over the back. I mean, I'm like 5 foot nothing. For me to get to the back, somebody's got to hold my ankles. All right? I'm serious. It's a huge handicap in this industry. And they put me in the trunk when they have an NVH noise. They got me to go for a ride. I'm the guy that goes in the trunk and listens for the noises. So anyhow, I put the FLS on the intake manifold. I grab ignition trace number 4 and I crank. I mean all the way out to here. Like I got 10 engine cycles on the screen, and I said this repeating over and over and over again. So I zoomed in on one event, but what I want on 2 full cycles here. So what I wanted to show you was this. First, look at these poles. Do they look even to you? Do they all pull down to that blue line? They don't, right? Clear as crystal. If you look up here, I wrote the specs that I measured for each valve, okay? Now, I'll tell you the intake valves were adjusted perfect. They were perfectly adjusted. The clearance were spot on. Why the intake valves?
They're easy.
Right, they're right on top. Nobody screws those up. They're the easy ones to get to. The exhaust ones, like again, somebody holds my ankle so I can get the ones behind the firewall or right in front of the radiator. Those are the ones everybody screws up because they're at a hard angle. So these specs here are for the exhaust valves only. Those are the only ones that had a problem. Now I'm going to zoom out here and see how this works. And those of you guys on camera, if you can't see this, I'll call them out to you. So somebody in this room, which one of these poles, let me do this. Which one of these poles does not pull down so deep? Which one looks pretty horrible? Pick one. 2. Okay? The lash on cylinder number 2 is 0. There was no clearance on cylinder number 2. Give me another bad one. 3. There's number 3 over here. That's pretty weak. The lash there is 1/1000. Give me a good one. What's a good deep pull? 4, 1. 4's got 11/1000 clearance and 1 has 10/1000 clearance. Ha ha! Doesn't that infer overlap? Which means we got valves that are out of adjustment, don't we? They're out of specifications. I don't know if the intake's too tight or the exhaust's too tight. It doesn't matter. Either way, that valve cover's coming off, right? But I can effectively determine that overlap is not right for some of the cylinders as compared to the others. So the intake poles identified properly and display a variation in breathability per cylinder. The breathing characteristics of one cylinder is different from another. Valve clearance is correlated to each pole, and it corroborates my hypothesis of excessive overlap affecting poles. Look at it now. I adjusted the valves. They look pretty good now, don't they? They're all set to specification of 11/1000. All these poles are about the same, aren't they?
The flat's a little wonky. We'll give you that.
Thanks a lot, pal. Everybody wants to point out my flaws. Story of my life. All these valves were adjusted to specifications. They all display the same pull. Now remember, these pulls are reflected by the cylinder's ability to draw on them. So just like we measure compression, if I had specifications that cylinder compression should be greater than 205 psi, and cylinder 1 was at 210, and cylinder 2 was at 210, and cylinder 3 was at 208, and cylinder 4 was at 209, would you make a big deal out of that? No. But understand there's some variance. That's what that is there. You got to stop picking the fly crap out of the pepper. But no, you make a good point. That's a good visual interpretation of what's going on. But my point is, they don't look anything like that, do they? We're good here. How do you think this car ran when I was done? Smooth as silk. So they were adjusted, the new cranking waveform acquired, confirms the fix, and validates my experiment. So I just learned something new that day. You have to play around with this stuff to learn from it. Valve clearance variations can be identified without disassembly. That's the takeaway from this slide. All right, let's move on now for a while to tailpipe waveforms. We talk about in-cylinder, we talk about the intake. Let's move on to the tailpipe waveforms. Cranking tailpipe waveforms will present differently than running tailpipe waveforms. So for the same reason, intake manifold vacuum looks different when cranking than when idle. Running waveforms are used primarily for misfire detection. The tailpipe is a very noisy area. There's lots of turbulence, there's cylinders pulling in and pulling out and overlap, and it's very disturbing to watch. But there is a benefit by looking at the tailpipe for misfires while the car is running. I only look at the tailpipe when the car is running to find a misfire. Otherwise, I'm looking at tailpipe pulls while I'm cranking. We're going to look for anomalies that differ from cylinder to cylinder. You know, it's like a lineup. We want to correlate these events to a suspect cylinder. This can be compared to the intake waveform for backup theory. So like I said, if I see something on the intake, it's just as easy to go to the tailpipe and see if my theory lines up with my tailpipe. There's 2 hours in the target then, right? Gives me more confidence to move forward. Again, just a piece of the puzzle. I never hang my hat on one waveform capture alone. So first we're going to see how the tailpipe waveform gets on the screen here. Now pay attention because this gets a little goofy. You gotta really pay attention. If I lose anybody and you guys at home, please write in the G so I can clear things up. The green trace is from a known good cranking in-cylinder waveform. The yellow trace is from not my FLS this time. We're using an absolute transducer. Leo, you asked what I like to use earlier. I prefer this. It's just as responsive as the FLS, but it's more stable. It doesn't have that flyback characteristic. You'll see here in a minute. The yellow trace is cranking tailpipe using the inches of water transducer. Again, an absolute sensor. Pressure forces the yellow trace to go north, just like an FLS, and vacuum forces it to go south, just like an FLS. So we got to remember this. When an engine's cranking over, we're going to have a little bit of seepage past the rings. That's normal blow-by. Again, it has to. If the rings are too tight, it's going to scuff the cylinder walls. We don't want that. We have to have a little bit of blow-by. That little bit of blow-by is going to cause this pocket differential. Now, I'm zoomed way in here. That's why it looks so extreme. It's not that bad. There's maybe 2 psi difference from here to here. But my point is, we do have a vacuum building in the cylinder. Now you guys will recognize this. This is a big cranking waveform, right? It goes up to here and it comes down, and here the exhaust valve opens. We go up on the exhaust, here the induction stroke, and then we come over here and we make another tower. You see that we're zoomed in here, right? You guys recognize where we're at? Here I'm showing -4 psi of vacuum. That's said another way, that's 8 inches of mercury. That's a strong vacuum. Until what happens? The exhaust valve opens, right? Where does that vacuum go when the exhaust valve opens? To the tailpipe, right? It introduces the vacuum to the tailpipe. That's what we have to keep in mind. Everything starts in the combustion chamber. So the cylinder under combustion has pressure upon the piston. This is a cranking engine. Otherwise said, no combustion, right? If there's no combustion in it, technically that's what a misfire is, right? So a misfire is going to look like a cranking event. You're going to have vacuum on top of the piston right before the intake valve opens. If this engine cylinder were firing, you'd see pressure. The chemical reaction causes that combustion event. The nitrogen, when it's heated, pushes the piston down. Right before EVO, there's still that combustion event sitting on top of that piston, at EVO. So a running cylinder has pressure at EVO, and a cranking cylinder or a misfiring cylinder has vacuum at EVO. Do you understand that significance? That's what's going to be in the tailpipe. That's going to help us determine if we have a misfire. You guys, everybody's heard of the dollar bill test, right? Right? We put the dollar bill in the tailpipe. Did anybody ever tell you why, though? Okay, good. Did anybody somebody told them that means there's a misfire, but they don't understand why? This is why. The vacuum in the cylinder, when it's introduced to the exhaust stream, causes that column of air in the exhaust pipe to pull backwards and suck back on that dollar bill. That's what we're going to look for here. We're going to use this test as an electronic dollar bill test, correlated to an ignition event. If we know the firing order, we know what cylinder's misfiring. So a misfiring cylinder is similar to in-cylinder compression characteristics. Again, the syringe analogy, the vacuum here. So check this out. So here, this is a zoom into capture. This is reflecting one full engine cycle. If you look closely here, top dead center would be way up here. We come down here on EVO. Here's our exhaust plateau. Here's the induction stroke, and we go back on compression again. We're zoomed way in on the bottom, just so you know where we're at here. What this is showing is how the tailpipe waveform and the in-cylinder waveform correlate to each other. Let me go back to this screen here. Right here, where the exhaust valve opens, we know there's vacuum in that cylinder, right? We open up the exhaust valve and the vacuum disappears, doesn't it? It goes to the tailpipe. Look at the yellow trace beneath it. As soon as this exhaust valve opens, the yellow trace drops, doesn't it? Meaning there's vacuum in the tailpipe. Come over here. As soon as the intake valve opens, vacuum drops, doesn't it, right here? The vacuum goes away here. The vacuum in the cylinder, the vacuum in the manifold is introduced to the cylinder where the exhaust valve is open. So here, we lose vacuum for a moment until when? Until the exhaust valve closes, right? That's what makes that letter M. Intake valve, exhaust valve open and it pulls down. Here, the intake valve opens, we lose vacuum. And then when the exhaust valve closes, we get intake vacuum back again. That's what causes that letter M. Does that make sense? And if you look at them, we're trying to correlate each one of these letter M's to each other. They all look about the same. That's what we're trying to do here. It's all the effect, the deep pulls, the long ones, right there and there, are the effect of EVOs. The little pulls, right there and there and there, are the effect of the intake valve open on the overlap period. Does that make sense? So when the intake valve opens, this drops to here. Then when the exhaust valve closes, we're not connected to the intake manifold anymore, right? So the vacuum goes away. And then this is the other pull from the next tailpipe, EVO opening. And that's why you get those letter M's, and that's why they all look the same here.
And this is strictly cranking, not running.
This is cranking, correct.
That's why they all look the same.
That's why they all look the same. We're crank, 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 crank. We're looking for differences there. I'm trying to show you guys how those squiggly lines get on the screen and how they all correlate to what's happening inside the cylinder. In-cylinder vacuum at EVO creates the tall pull on the exhaust, the deep one, right here. Okay? Right here, right here, right here, right there. The tall ones. That's from EVO. Manifold vacuum applied to the tailpipe due to overlap when the intake valve opens causes this one here. Boom. Then the exhaust valve closes and vacuum goes away. That's due to overlap. Again, the colored boxes are just there to show uniformity from each group of pulls. And there's one highlighted and annotated on the left, and there it is undoctored on the right. So I want to show you something here. Talk about correlating, looking at all the cylinders' contribution to the tailpipe. Here's what I see here. All the tailpipe, if this is the EVO, the vacuum at EVO, right? The in-cylinder vacuum buildup right before the exhaust valve. And I just told you, as soon as the exhaust valve opens, the vacuum's introduced to the tailpipe here. That's a tailpipe pull, that's a tailpipe pull. They're all about the same except for this one, right? And it repeats itself 1, 2, 3, 4, 5, 6 events later. That's from the same cylinder. What that means here is the cylinder that made this pull in the tailpipe has a deep pocket here, doesn't it? And what does a deep pocket mean when we have pocket differential? Leakage. This tells me one of the cylinders has leakage. Does that make sense?
Yeah.
So go ahead.
The cylinder that, like your in-cylinder, your green trace there.
The green trace made this.
Yellow pulse right after it is exactly from that cylinder.
That's it. Watch. If I took a line here and drew it straight up.
Okay. I just didn't.
See how that pull?
Not a delay like on the intake, right?
That's correct. You're seeing the pull instantly.
Okay.
Okay, so check this out. If this green trace is cylinder number 1 in cylinder and the firing order is 1, 4, 2, 5, 3, 6, EVO number 1, 4, 2, 5. This would be EVO for number 3. Now I'm going in cylinder number 3 to see what's wrong. Does that make sense? Or I might go to the intake manifold now and repeat this test and see if pressure's going into the intake. In 2 tests, I knew I had a leaky intake valve, don't I? And I didn't even take a spark plug out, did I? How long did a cranking tailpipe test take? 10 seconds. How long does a cranking intake waveform take to grab? 10 seconds. In 5 minutes, once you get good at this, you have an engine analyzed and diagnosed and you didn't even pull a spark plug out. See what I'm getting at? When you get good at this and you start practicing. So all tailpipe pulls are compared to one another, and there's one considerably deeper pull as indicated by these red circles here. This indicates that cylinder has a loss of volume. Not the green one that's on the screen, but the other one here, a different cylinder, has a loss of volume. And I saw that all through the tailpipe. This is caused by deep exhaust pocket venting to the exhaust during EVO. So here's one here. The car I'm working on here was a 4-cylinder Toyota Camry. It was towed in off the interstate. The guy was riding from upstate down south. He was on the highway for hours with no drivability faults. He pulls over to a gas station to take a whiz and get a cup of coffee, and he gets back in the car. He did refill it with gas. Crank, 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 crank. It wouldn't start. He had the car towed to us, and I get the car, and I did experience the same thing. Crank, 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 crank. So crank, no start condition. Now listen, I put a 5-gas analyzer in the tailpipe, and I had a boatload. I mean thousands of HCs, like 10, 20, 30,000 HCs. But I had no CO, and I had no CO2. What didn't happen in those cylinders? Combustion. Combustion did not happen. So if I have fuel, and I have no combustion, it's likely I don't have spark. Wouldn't you agree? If timing was off, I'd have combustion. It might not be that good though, right? I'd still have traces of carbon monoxide or carbon dioxide. I got nothing. So the 5-gas analyzer showed me I have a lack of spark. But I pulled all 4 of the cops. Remember, I always configure, my diagnostic approach is based around the car I'm working on. And this has a cop ignition system. It's easy for me to zip 4 10mm bolts out and flip these cops upside down. So I took an adjustable spark tester and I cranked this engine over, and all 4 cop coils produced a ton of spark. I mean, good, strong spark over a huge gap. So now I'm getting confused. So I thought, I have fuel, I have spark. The only thing left is cam timing. So I did a check in cylinder of cam timing, and it lined up. So it proved timing wasn't an issue, but I inadvertently found out what was wrong with this car by accident. Check this out. So in cylinder, you could recognize in green here, of course, we're zoomed in on the bottom now. We see we got compression. It's clear to see the towers are leaning. Can you guys at home see that? Yeah. If I drew a line down the center of this, that green trace looks like it's going like this. Leaning tower, deep pocket differential. What does that mean? We're leaking compression somewhere. Not that we talked about this yet, but this blue trace are intake poles. A pole, a pole, a pole, a pole. We can see they're all the same. The yellow trace is my tailpipe poles. I have my inches of water transducer in the tailpipe, just like an FLS. So what I see here, first of all, as far as valves opening and closing, we see a nice crisp transition from here to here, don't we? Sharp opening, sharp closing. Exhaust valve opens, intake valve closes. The valves seal just fine, don't they? We don't have valve sealing issue, but we do have cylinder leakage. I see the tailpipe pulls here. Check this out. The deep in-cylinder vacuum is vented to the tailpipe when the exhaust valve opens. Boop. That's the pull there. This pull and this pull and this pull and this pull are all the same. So is it necessary for me to go into all 4 cylinders? If this cylinder looks good and they produce the same tailpipe pulls, I know the other cylinders are in the same condition. More importantly, I just thought about the fuel. That excess fuel from lack of combustion would crank and wash the cylinder walls down. That would cause cylinder leakage, wouldn't it? That's what's causing this. So then now back to the story here. I'm like, okay, wait a minute. I got spark, I got a ton of fuel, timing is good. Now I have washed cylinder walls, and that's why I have no combustion. The spark plugs are wet. Let's dry everything off and get it going. So I dried everything off and put it all back together. Again, crank, 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 nothing. I pulled it back apart, dried the spark plugs again, and put it back in, but this time I was smart. This time I used my head. The only thing that changed from the time those cops were in the cylinder versus out of the cylinder is their proximity to the cylinder head. I took some high tension leads and went between the cops and in series to the spark plugs. What I did was I allowed them to reach the spark plugs, but without being in the cylinder head. Now this thing coughed and blew smoke like crazy for a few seconds, but I did get it running, and it started and ran great. As soon as it started and ran, I put the cops back in the head, cranked the engine over, nothing. What are the odds that all 4 cop coils burned through simultaneously with no drivability symptoms leading up to that event? Slim to none, right? Now you can see why I deviated. But my point is here, I'm always learning. Every step of the way I'm learning. I've never seen the results of washed down cylinders before. Now I did. I posted this immediately on Facebook chat groups and stuff. I'm like, hey guys, look, this is what washed cylinders look like. And the takeaway is huge loss of compression, leaning towers, big pocket differential, but the takeaway is the valve events look great. This is exactly what blow-by looks like too. Do you guys, did I lose you on that one?
What happened with the coils? That's where I got lost.
The coil, what?
They were looking for a boot to the cylinder.
Yeah,
Oh, okay.
they working.
Okay.
Go ahead, up here.
Brandon, last night when you said that, Jerry and I were talking about it. Those coils could have had really weak insulation, and the guy maybe hit the gas and it ran lean and had a real high, a high voltage blow-through event
Due to
on the
lean.
startup.
Potentially, and you know what? When I asked this guy if the car ran good, maybe he was driving like a grandma for 460 miles. You know, we get in there and go like that, and maybe it would have went blup, blup, blup. You know what I mean? It might have been running bad, but he doesn't put it under that kV demand to force those sparks to deviate. So those are all valid points. But he led me astray from the data he gave me. So the green trace, again, is in cylinder. Yellow trace is cranking tailpipe. The large pocket differential, 16 inches of mercury difference there. That's 8 psi difference. Huge. It should be around here, like 2 or 3, caused by the fuel washing the cylinder walls down. Defined valve events, leaning towers, reflected loss of volume. The stored vacuum in the cylinder was vented during EVO, and that's what caused those deep exhaust pulls, encircled in red. This reflected as a pull in the tailpipe, as pulls in the tailpipe waveform. The leaky cop boots were the root cause. 4 new coils fix this. Again, overlap. It plays a role here too. Valve overlap is a duration of time when both the intake and exhaust valves are open simultaneously. It essentially links the intake to the tailpipe and the cylinder. Overlap reflects in the pushes and the pulls because of pressure changes. Excessive valve clearance decreases duration of overlap, and tight valve clearance increases duration. So check this out. We talked about the letter M, okay? I don't know if you guys at home can see this piston chart. I know it's a little washed out because I have the transparency turned down. But what we're seeing here is the effects of EVO. So check this out. Cylinder number 1. Let's go to cylinder number 4. It's easier to see. Here's 1, 4, 2, 5, 3, 6 in the firing order. Here's compression. Right here is our induction stroke. Right before we go into the exhaust stroke, about 45 degrees ahead of time, our exhaust valve opens. That's what creates this pull here, okay? Let's go over here to this letter M here. This is the overlap period for cylinder number 1. The intake valve opens. We're still connected to the exhaust, so that happens there. But then the exhaust valve closes, and we get that pull there. So we're looking for that letter M, and what we're looking for when we're comparing overlap scenarios, tailpipe pulls, to the cursors is we want to see how close this point is to this cursor. And we want to see how close this point is to this cursor. And we're going to compare all these points. Uh-oh. You see these 2 cylinders? There's no letter M there, is there? We've got an overlap issue on those 2 cylinders. Guys, I use this as an upsell technique. You guys pull in 3,000 mile services and pull the air filter and go running up front with a dirty air filter. While you're doing that, I'm going to the tailpipe and I'm cranking the engine over. And I sell valve adjustments this way. Not to make it about money. This is a 4.5 hour job on a V6 Honda. I got so good at these, I got them down to about an hour and a half, okay, once the engine cooled off. And I was making money hand over fist upselling valve adjustments. People run from these things. I was begging for them. Okay, you clearly see the difference? A letter M, a letter M, a letter M, and then we get over here. And the lady didn't realize this. She was driving the car for so long like this, she just thought that's how it runs. Check this out. So the green trace is the FOS in the tailpipe. I'm cranking the engine over. The top of the waveform displays the results of valve overlap for each cylinder in turn. This exhibits differences in the valve overlap per cylinder. This indicates the valve clearance adjustment is required. Check this out. Now look at them all. I'm looking where this point falls relative to the vertical cursor. It's in black, so you guys at home might not be able to see it. This trace, here's the vertical cursor. The proximity to the vertical cursors are the same for each event, meaning all the overlaps are exactly the same. Food for thought. We've had hydraulic lifters for how many years? Why do you think Honda uses adjustable lifters? To maintain the correct overlap. You can't guarantee that with hydraulic lifters. They collapse, don't they? They wear out. You can maintain overlap if you have a mechanical link, not a fluid coupling. They want to see this letter M. They don't tell you and me that. They say adjust it to this clearance. What they're really saying is make the overlap this much. How do you think this car ran when I was done with it? Smooth as silk. The overlap for every cylinder was the same. Its breathing characteristics was the same. If I could take 6 cylinders and make them all identical, the chances of this car running smooth when all those cylinders complete a combustion event are a lot greater than when they look like that. because the breathing characteristics, their ability to fill with a fresh air charge are different. So valve clearance was adjusted to spec. Overlap events are now occurring at similar times per cylinder relative to these vertical cursors here. That's what we're looking for. We want to see how close this event falls to that cursor, how close that event falls to that cursor. When you have adjustment issues, they start spreading out or getting closer. That's what we're interested in. Again, our bad cylinders were over here, cylinders 2 and 4, but they're fine now. Pressure changes represent the opening and closing of both the intake and the exhaust valves. This is all detectable through the tailpipe without disassembly. Great upselling technique. Oh God, we're running out of time here. I'm going to blow through this here. This is a piston chart. If you guys can hang in there 5 more minutes. This is a piston chart. This helps us make associations with what's going on with the engine and compare it to the 720-degree engine cycle. Okay, we're going to recap on this when we come back, but I'm going to blow through it. This is it attached to an in-cylinder waveform. Again, we can see the exhaust valve opening here. This is cylinder number 1. Here's how we use the chart. Power stroke, exhaust stroke, EVO occurs about 45 degrees before. It lines up perfectly with that piston, with that in-cylinder compression waveform. Here's how we use it on the tailpipe. The yellow dots that I put on here indicate where the EVOs occur for each cylinder. So here's cylinder number 1. You can see EVO occurring just before bottom dead center. Same with cylinder number 8, 4, 3, 6, 5, 7, and 2. They correlate with these poles here. What I'm getting at is this. If cylinder number 7, I did a relative compression check, and cylinder number 7 was a dead hole, crank, 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 and I went in the tailpipe. If cylinder number 7's exhaust valve was compromised, what should I see in the exhaust stream when cylinder number 7 approaches top dead center compression?
Less pressure.
More pressure, right? Look here. Cylinder number 7, I know from a previous test that 7's a dead hole. If I come over here to 7's compression event, here's bottom dead center, here's halfway up, here's top dead center. You see all this noise in here? It doesn't look like these other letter M's. This is all noisy because there's extra exhaust content being forced through there. That confirms cylinder number 7's dead hole is a leak on the exhaust side. I have enough evidence to convict here, but I'm still going to grab an intake waveform. Okay? Does that make sense how I did that? So the piston chart helps identify the EVOs and compromised valves receipts. I'll use it as a follow-up to relative compression testing. A push at TDC for a suspect cylinder indicates exhaust valve sealing issue. That's what we see right here. It helps corroborate theories without disassembly. Here's an intake side. Again, the yellow traces, the yellow dots that I put on the piston chart myself indicate when the piston starts to pull down on the intake manifold. We open the intake valve here and the piston starts to pull down. It creates this pull here. So let me give you a scenario. Crank, 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 crank. I got a dead hole and it's cylinder number 5. If I'm looking at the intake manifold and I go over here and I look, where's the pull for cylinder number 5? The pull is right here. If the pull is good, think about this. If I have a hole in a piston, can that piston pull good on the intake manifold? It can't. If I have an exhaust valve that doesn't seat, can that piston pull on the intake manifold? It can't. So if I have a good pull for number 5, what does it say can't be the problem? It can't be an exhaust valve and it can't be a hole in a piston. What's left? Could be an intake. Let's come over here to compression and confirm that. If it's my intake valve, what's going to happen to pressure in the intake when my dead hole comes up on compression? Okay, there's at that same time, another cylinder is going to be on the induction stroke. Remember, one girl's pulling on the straw, one girl's spitting back in the cup? So I find number 5. I find number 5's compression event, which is right here. Top dead center compression. Uh-oh. Is that pull weak?
Yep.
What does that say about number 5? Where's the contents going? Intake manifold. See how easy that is? It's that simple. We're going to blow through this. Let's get to a case study. Crankcase is simple. If you see compression going up on a dead hole and your pressure in your crankcase is going up, you got blow by.
Yep.
You guys got that, right? Let's keep going. Cooling system. Car's overheated. Could be a stuck thermostat. Let's say the thermostat's the root cause, but it already ruined the engine, and it pays 6 hours to do the thermostat. What's that one GM engine where you got to go around the back side, the passenger side of the car, and the thermostat's on the back of the head? That one GM motor, it's a newer one? I can't think of it. It was a real pain in the ass to do, pardon my French. But what if that thermostat was no good? And I go through all that, and I get it back together and burped, and I drive it, and the son of a gun's overheating because it already ruined the cylinder head or the gasket. I can do this test, put my first look sensor or my inches of water transducer in the neck of the radiator, not in the fluid, but in the air on top of the fluid, and crank the engine over. If I see a pressure spike, I can then throw up an ignition waveform so I can correlate with a piston chart and find out, look, cylinder number 4 is heading up on top dead center compression right here, and it made the spike go up. Cylinder number 4's cylinder is leaking to the cooling system. Make sense? Simple as that. Let's keep going forward. There's another one. Relative compression check using an air probe is in green. Here's my dead hole. We can all see that, right? Yeah. This is cylinder number 1, 42536, 1, 42536, 1. Number 1, this blue traces my FLS in the radiator. Every time cylinder number 1, the one with my dead hole, comes up on compression, pressure in the radiator goes up. You see that? Let's move on to a case study, okay? That's just a zoom of it. If I lost anybody, please write in. My email address is on the back of that, of your information packet, so anybody can call or get a hold of me and I'll answer any question you have. We're going to blow right through this. We talked about the piston chart. We ran out of time. If anybody has any questions, like I said, email me. I'll gladly answer any questions you have. We can use some math. Okay? Use some math to figure out the same thing the piston chart's going to show us. Forget the shape of the waveform. We're not analyzing the waveform. I'm going to show you guys real quick how to use the cursors to do the same thing the piston chart does. We're going to associate time with the 720-degree engine cycle. So what I'm going to do is put one cursor here and one cursor here. We know that's 720. It took 107 milliseconds to go 720. If I divide 107 milliseconds into the 720, I get 6.7 degrees per millisecond. Here's what you do. You scratch that down on your repair order and you write it up here and you save that. I mean it. You write it on the repair order and you throw it to a side or a sticky notepad because you have some more math to do. That's one function of the math equation. Then you take that 107.82 elapsed time that you had here, okay, and you're going to divide it by 4. 1, 2, 3, 4. Otherwise stated, multiply it by 0.25, 25%. What that tells me is that's where my 180 cursor goes, where bottom dead center is. It goes at 26.95 milliseconds. So I leave the first cursor there. I move the second cursor over until my delta time is 26.95. That's 180. Then I can take my first cursor and move it to, let's say, EVO. And then I say that delta time right there is 506. I multiply that by the number that I told you to scratch down. Okay? That'll give you 34 degrees before bottom dead center. You see how easy that was? Yeah. Take some practice, but you understand the math. Okay? If you wanted to find the 360, you don't multiply by 0.25, you multiply by 0.5. If you wanted the 540, you multiply by 0.75. 25%, 50%, 75%. You got that? Let's keep moving. I want to get to a case study. Spark advance the same way. You find 720. You divide that into 720. You get 4.1 degrees per millisecond. You multiply the elapsed time between when spark discharged and TDC. You get 2.43 milliseconds. You multiply this by that. 10 degree spark advance. See how I did that? It's that simple. Connecting the puzzle pieces. That's what we're trying to do. It's the name of the game. Mechanical testing is driven by generalized tests. I'm trying to get into a funnel. I'm trying to move down these funnels towards the problem. Every test I do is justified by the test before it. Relative compression check is what I'm talking about. We do an RC test first. This leads me to my dead hole. My dead hole in this case is cylinder number 4, cylinder number 1. I know number 1's my problem. I'm always asking myself, what's my number 1, what's my dead cylinder doing in any point in the waveform I'm analyzing? I know we're breezing through this. Just bear with me. Now, let's get to a case study. If you guys can hang on 10 more minutes, we'll get through this. These are real case studies from my own work bay, okay? 2003 Buick Century. The vehicle exhibits a misfire and poor running condition. It exhibits abnormal cranking cadence, dead hole. I can hear it with my ears. Relative compression check for the starter current was performed to isolate the offending cylinder. Cylinder number 6 is an ignition waveform right in the front of the motor. It's a GM V6, so I use that one because I'm lazy. There's 720. There's the firing order. Cylinder number 2 is the one that correlates with this low peak. We know that to be my dead hole. Agreed? Okay. Any ignition event was chosen for reference is acceptable as long as I know the firing order. Cylinder number 6, ignition trace was chosen for reference. It's easy to access. The results of the relative compression check yielded cylinder number 2 as my suspect cylinder, the one with the dead hole. It took a minute to perform, holds high value. Where do we go from here? We could go in cylinder at this point. We have enough evidence to convict, but I'm still trying to learn, and I urge you guys to do the same thing. Gather as much data as possible and crunch everything together. So we're going to go in the intake manifold now. Okay? We're going to look for the poles and compare them from one another. Look for the odd man out. So there's where I sampled from. Those of you guys recognize your standard GM V6 engine. There's a vacuum T right behind the throttle body, perfectly centralized. So that's where we're going to hook up our vacuum transducer. Okay? We crank the engine over. This is a waste spark system, so I get a firing event for compression, I get a firing event for waste spark, and I get a firing event for compression. Here's 720 from here to here. We can see the intake trace repeating itself. The blue trace is an intake manifold. It's a vacuum waveform. Okay? It clearly displays uneven pulls from one cylinder to another. Vacuum makes the blue trace go up. Remember, vacuum transducer. Pressure makes it go down. We're going to dissect the waveform into 6 equal parts. Why 6?
6 cylinders.
6 cylinders. We want to see how each of the 6 cylinders is affecting the intake manifold. So I drop the cursor there, I drop my cursor there, I press mark cylinders configured for 6 cylinders. 1, 2, 3, 4, 5, 6 partitions. Every upward going pull, every upward going sweep is a pull from a piston. This is upside down to what you're used to looking at. We're going to apply a piston chart here to help us aid in analysis here. So the yellow arrows indicate the pulls. What we see here is the blue vacuum trace is ascending as the contributing pistons pull, indicated by the yellow arrows, a pull, a pull, a pull. What we can see here, if you look closely here, the red trace, where'd it go? That red, see all the arrows, guys at home? That's a pull, that's a pull, that's a pull, that's a pull, that's a pull. Number 2 is not pulling. Consequently, number 2s are dead hole also. Don't forget. We also see this, the pulls are getting really strong here. I don't know why yet, but we're going to talk about that in a second. Okay? The trace displays a lack of pull in cylinder number 2 intake stroke. Right there. All these show pulls. The red one does not show a pull. And again, that's the hole that's dead. The intake stroke, what's the significance? Let's move forward. Now we're going to go in cylinder and put the 3rd arrow in the target. Now, I had to back this car out so I could do an oil change, and then I pulled this car back in. Where you guys saw the blue trace before, now there's a yellow trace in its place. It's the same trace. Ignore the red one. That's in the tailpipe. We're not looking at that. But you guys do recognize something here, don't you? Nice and round. What's that say about the intake valve? It's not open. And if the intake valve doesn't open, wouldn't that line up with the fact that we can only make 12 PSI compression? What would that do to the starter? The noise. Dut, 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 dut. Sound like a dead hole. More importantly, this is our vacuum trace. Now the engine's running. Okay, the engine's running right now. We got stored vacuum here. Every cylinder contributes. Remember the girls pulling on the straws? Everybody takes a turn pulling. What if this guy doesn't pull because the intake valve doesn't open? Don't we lose vacuum here? When does vacuum come back? When the next cylinder pulls, right? That's why vacuum dips here. We lost vacuum. The very low compression of 12 psi, it explains the cranking cadence we heard with our ears. There is no indication of cylinder leakage, is there? Straight towers, even pockets, right? No leakage. The rounded intake pocket pinpoints the lack of intake valve opening and the reason why we have low compression, 12 psi. There's nothing to squeeze. The cylinder cannot inhale. Okay, we had justification to remove the front valve cover only. We didn't have to take anything else out. We know where bank number 2 is, we know where cylinder number 2 is, and we know we're going for an intake valve problem, don't we? Intake valve rocker threads pulled out. This is a common problem, we know that, but we're doing some analysis. We're riding with our training wheels on, right? Let's go back to this for a second before we go. Guys, hang in there, 5 minutes. Let's go back to this. If vacuum's going up, why does vacuum increase and then decrease here? Let's talk about this for a second. That's where the piston chart comes in handy. What's our dead hole? 2. Where's 2 go up on compression? Here's number 2. 6, 1, 2. 2 goes on compression here, in this area here. What happens to crankshaft speed when number 2 goes? It goes faster, right? Wait a minute, this is a whole engine. Aren't some cylinders on their induction stroke? If I got my syringe here and I'm pulling a vacuum and all of a sudden I go like this, what happens to vacuum in that syringe? Really deep. So here's what happened. Vacuum got really strong here and even stronger here till when? Till the next cylinder, cylinder number 3 came up on compression. That crankshaft took off like a bat out of hell, right? And then what? It hit a wall. The rotation speed went up, which caused that to happen, and then when the next cylinder came up on compression, the crankshaft did one of these and slowed down. And vacuum dropped because the crankshaft slowed down. Does that make sense? Yeah. So we know what this is due to crankshaft speed, and we had no vacuum contribution here from number 2. Why? Because the intake valve doesn't open. Is this hard? This is easy. This is really, really easy. All you have to do is understand it and practice. Does that make sense? Awesome. Guys, thank you so much for coming out. I really appreciate it. We are going to be back here. I can't promise you a date yet, but sometime within the next season. Right, G?
Yep. So our season ends in May, but starts up September, October, November, we're off December, and then we go back into a January, February thing.
Okay.
Big event in March, so we'll work
Excellent.
something out, getting you back.
Great, guys. So I look forward to coming back. I hope you guys took away something. Again, if anybody has any questions, my contact information is on the back of your workbook. You can reach me by email, and if we have to have a phone conversation at that time, I can give you my number. We can talk. Guys, thanks so much for tuning in at home. I really appreciate it.
You guys can fill out your evaluations, leave them here, please. Pick up your cups, throw them out if you don't mind.
Can I use your pen, Jay?
Sure. Yeah, that's Leo written all over it.